Уважаемые организаторы, можно будет поговорить? Господин Зверев, можно с вами поговорить? Алло.
Да, вы меня слышите?
Да-да, здравствуйте. Это Ашуров вас беспокоит из Ташкента.
Ага.
Ну, я сейчас в данный момент нахожусь в другом городе Узбекистана. А вот только что мне сообщил Аксенгеллер, который должен выступать в 11:20.
А,
Вашему...
да-да-да, до меня дозвонились. Мы вопрос уже решили. После 12 часов я сообщу, когда он сможет сделать доклад. Вот, если
Да,
это...
дело в том, что там, оказывается, в районе отключили, там какая-то авария произошла.
Да-да-да, мы
То
уже...
есть вы в курсе, да?
Да,
Можно будет, да?
да-да-да.
Потом. Спасибо, тогда мы пока выходим.
Мгм.
Спасибо.
Да, до свидания.
А у вас что, сейчас перерыв, что ли? Нельзя,
А,
например,
Просто
слушать?
секция еще не началась. Там немножко задерживается на 5 минут.
Ага, все понятно. Спасибо большое.
Ага, до свидания.
dear colleagues, I think we are ready to start our session. First talk will be presented Professor Tsvetkov. Disclosures with the off-axis beam path in degenerated type cavities.
Good morning, ladies and gentlemen. Despite of the fact that all of the participants are from the Russian part of our community, I will do the talk in English as it is done, all the talks at our conference. In my talk, I would like to describe the operation of disc lasers with a special operation mode in degenerate type laser cavities. This is how it should change. Okay. This talk is as a review of such an operation, and the most interesting operation mode, disc laser with several lines output, will be presented in a talk by Denis Guriev later. And first of all, a few words about the goal of the research, about the motivation, and then the description of the experimental results of the disc laser with single beam and multi-beam pumping, with off-axis beams, with narrow line output, and with several lines output. Next, please. First of all, about the goal. Our goal is the development of solid-state lasers, which can operate in different modes, and first of all, oriented to the special output characteristics such as spatial, temporal, and spectral one. Next. One of the problems of the creation high-power solid-state lasers now is mainly solved. Everybody knows the disc lasers produced by the Trump company with several kilowatts output. And now only very interesting, but only technical problems should be solved. But the problem of the development of microchip lasers with special output characteristics is in progress now. And on my mind, it's more interesting than the high-power lasers. Next, please. First of all, about the active media. We made the experiments in 1 micron spectral range. It may be done in any other spectral range, but we were oriented to understand the features of laser operation, and in 1 micron range it is easier to obtain. So we may use both ytterbium doped or neodymium doped active medium. It doesn't matter from the point of view of the pumping efficiency. You see that absorption coefficient is very near in all the active media. These diagrams were taken from the publications, and you could see that they differ from the real absorption spectrum, because the line is wider than in reality, but this is oriented for understanding the absorption when you pump with the laser diodes, with the wide enough spectrum, about from 2 to 5 nanometers. And in this case, we achieve a less absorption coefficient than for the narrow line pumping. So real absorption coefficient for neodymium yak about 8 back centimeters, for yttrium vanadate about 40, but only for one polarization. If you use the diode laser for pumping with the fiber output, then we have the unpolarized emission, so the average absorption coefficient is less, but it's enough to provide almost the total absorption of the pumping emission on the double pass of 1 millimeter thickness of the disk. Next very important point is the heat spreading in the active disk. You know that if the disk is very thin and the material possesses a high thermal conductivity, as for example yak or vanadate crystals, then we can achieve unidirectional heat flow. But if you have thicker disk or lower thermal conductivity, or the sizes of the pump spot is comparable with the thickness of the disk, then we should take into account the lateral heat flow. And you could see at these examples that when we have 1 millimeter thickness of the neodymium doped vanadate disk, then with the diameter of the pump spot near to the thickness of the disk, the spreading of the heat flow, lateral spreading, is big enough. And when we use the bigger size of the pumping spot, then the heat spread is nearer to the unidirectional heat flow. Next one. Why we are interested so in this heat spreading in the disk? Our first idea was to change the one-point pumping by the multi-point pumping of the disk. In this case, we may produce more homogeneous heat spreading over the disk surface, over the disk volume, and when we achieve the coherent beam combination of all these different beams, then we can achieve high average power in the output and together with high beam quality. Next, please. This is an example when we arrange our pump points in a line, and you could see with these interference figures, which shows you that optical path difference along the optical axis is lower, of course, than in the perpendicular one. This is the confirmation of that our idea may work and may be useful for achieving the high power operation. Next, please. But you see that if you have a number of pumping spots, we have the beams inside the resonator, the intercavity beams, which becomes the off-axis beams. The first idea of the laser cavities with off-axis beams was proposed by Kogelnik in the middle of 60s, and in the end of 60s it was calculated very thoroughly for different organization of the spots around the mirrors by Ramsey. What is important? All these calculations and all this demonstration of such an off-axis beams was done in demonstration in gas lasers, and calculations were done for the empty resonator. It's important because if you use solid-state laser, we never work with the empty resonator. We should take into account the thermal effects in an active media. Next, please. What does it mean, degenerate or non-degenerate laser cavity when we use an off-axis beams? If you have the possibility when the single intracavity beam may have a closed optical path, it means then if it starts from one position, then after several integral round trip over the resonator, it comes to the same point. So we may have the degenerate laser cavity. If not, we have non-degenerate laser cavity. Why it is? It means it may be shown that if we have this n round trips, then every n mode possesses the same frequency than the previous one. So it means that we have the degenerate lasing. But it is possible the operating of such a laser in non-degenerate mode. It was shown by Malutin about 15 years ago because the separation between mirrors in non-generate and degenerate resonators are very close. And if we have non-degenerate lasing, even in this case, we have some overlapping of the beams and the lasing may be done. Next, please. If you look to our experiment with the line of the pumping spots, we may achieve that they produce the optical path changes over this line. And you could see that the optical path changes in the middle of the pumping area is twice bigger than in the outer space. We take into account only the optical path changes and we don't think about the physical mechanisms which produce these changes. The main is bending of the thermally loaded disk, then the common thermal length arriving due to thermal changes in refractive index and in the disk thickness and photoelastic effects. And the last one, changes in refractive index due to the changes in the inversion population, so-called electronic lens. We should remember this difference in the optical path when we go to experiments. Next, please. If you have such a pumping figure, then, as I told you about non-generate and degenerate laser cavities, in non-degenerate, we achieve in the far field this type of interference figure. It means that all the spots produce their own beams, but due to partial overlapping of the neighboring beams, we have the situation where the phase difference between different laser beams was conserved, but not all the beams are in phase. So we achieve so big size of the output beam and this type of interference of all the beams. If you go to the degenerate laser cavity, in what the only intracavity beam goes through all the pumping spots, and it makes the synchronization of all the output beams and produce the coherent beam combination and produce a very high beam quality in the output. Next, please. At the first experiment, we use the output mirror with the homogeneous reflection coefficient over the mirror surface. But we may use another thing. When the part of the mirror is high reflective and only part of it is output coupler. In this case, we can organize only a single beam output and the lasing only by the single intracavity beam. This is so-called VW configuration of the cavity, of the degenerate cavity. And the adjustment of the cavity sizes to the separation of the pumping spots may be done by rotation of the output mirror. You see that it may be adjusted to any shift between the pumping spots. Next, please. If you operate in this, with this laser cavity, we obtain a very stable output characteristics in divergence. And this divergence angle corresponds to the fundamental mode divergence in all the range of the pumping power. You see, of course, it's not a kilowatt range, but for a case that we have a thick enough disc of 1 millimeter and not a good interface, thermal interface between the disc and heatsink, so it's a very good situation. Next, please. In our experiment, we use another type of the cavity, AMP type, where we have another parameter of degeneracy. This is 4, and in VW laser cavity it is 6. And the less parameter of degeneration, the more stable this cavity operates in degenerated mode. The same, this cavity may be adjusted by the rotation of the output mirror. Next, please. We used these cavities to achieve a single longitudinal mode lasing. In M type of cavity, it is easy. In VW cavity, it was more difficult because very often we obtain 2 longitudinal modes because it's more sensitive cavity. Nevertheless, we can obtain a very narrow line. I can tell that this is only the spectral resolution of the Fabry-Perot interferometer with 4 centimeters base. Next, please. Next question was how to achieve two nearest spacing between 2 lines, because the degenerate cavity may be organized for lasing not in only single longitudinal bot, but in 2, 3, and more. But they are spaced in our condition by 1.5 of gigahertz, and if we want to achieve less spacing between output lines, you will try to achieve the lasing in neighboring transverse modes with the same longitudinal mode. We achieve it while pumping by elliptical spot, and we achieve the lasing in 2 output transverse modes, the fundamental one and TEM10. And this is very interesting because these modes are coherent. And next, please, we can achieve a mode beating in the output. When we analyzed this signal with radio frequency analyzer, we achieve a very exact data for the frequency of the beating, which is equal to the mode separation, the calculated mode separation, but much more interested that the width of this line is 3 kilohertz, which is 4 orders of magnitude less than we obtain with the Fabry-Perot interferometer. And a real line width may be more or less, because 3 kilohertz is the resolution of the radio frequency spectrometer what we have used. And now we come to the summary. Next, please. In summary, I would like to tell that the use of the disk with multi-point pumping will give us the possibility to develop the high-power lasers, which is pumped by the multiple point and produce very good spatial characteristics output due to coherent intracavity coherent beam combination. Moreover, even in the mode of operation with a single output beam, we achieve a very stable fundamental mode operation in a wide range of the pumping power. Of course, this is a source, robust source of a narrow line emission of a single longitudinal mode. And the next one, that disk lasers with degenerate cavity may serve as a radio frequency source in the range of several hundred of megahertz to several tens of gigahertz. But about this, it will be talked later. Thank you very much for your attention.
Thank you, Speaker. We have time for one short question, if you have. Okay, let's thank Speaker again.
I tried to tell very exactly. Thank you.
So, the next talk should be in online regime, but I don't know what about connection. So, okay. It's a third speaker, correct? Professor Schur. Call her.
Some technical problem.
Sure. Oh. Please note that this is a third talk in our program. And please follow the time, follow the rules of our session, please. 20 minutes.
It's a great pleasure to be here and to speak about some activities which is connected to application of ferroelectrics in preparation of different devices, very important for optical applications. In this case, I will speak about two of them. One of them is optical converters, which is possible to change practically any frequency to any. Just now it's wide range of frequencies. And also about some tunable diffractive elements which can be produced also from this very interesting materials. It's well known. Let's next. Wow. Next. So the idea about phase matching was published many years ago. And even more. So it's very, very important publications of Nobel Prize owner Niels Blombergen, who have discussed different methods of phase matching. And in this paper, which have been written year after, you see, the first, second harmonic generation, and at that time he proposed one of the possibilities to prepare some periodical structure. At the beginning, it was a structure which is some thin plates of materials which rotated axis. Next. But in a short time, R.C. Miller proposed application of ferroelectric domains in this case. So it looks like such a possible solution. But the problem was that in this case, it was necessary to have the reproducibility of period in tens of nanometers. So for many years, it was only, you see, idea, but not a realization. Next. So the idea was very nice, and this is the parameters which can be done. In this case, it's necessary to have a periodical structure, periodically pulled crystals, which is now, but it was very difficult to do that. Yes. Next. It's wide applications of it. It's second harmonic generation. Next. Optical parametric oscillation. Yeah, and also it's possible to work it in terahertz and in difference and some frequency generations. Yeah, so in this case, people come to domain engineering. Yeah, and this is two persons, you see, from Penn State University, from Pennsylvania, yeah, who have proposed to, you see, the idea of domain engineering, so preparation of proper domain structures in ferroelectrics to improve their properties. At the beginning, next, they speak about application, it's in piezoelectric properties, yeah, and acoustic devices. Next. Yeah, so such a structure, this is a typical one, this is line domains, stripe domains. Yeah, but it's possible to have different shapes of such a domains. Yeah, so materials which people use now, lithium niobate, lithium tantalite, KTP and KTA crystals. Yeah, it's just, and the periods from 30 to 4 microns, yeah, which is allows us to produce all the wavelengths in the, from violet to infrared, yes. Next. Yeah, the problem, next, yes. How to achieve the submicron domain periods. Yeah, and this is, next. Yeah, so in this case, it's necessary to have nanoscale period reproducibility. Yeah, next. You see, it's the first people who have done one of these results. Yeah, it's a famous Ginston lab in Stanford University. It's a pleasure for me to work with these people and with the previous two. Yeah, it's a great experience of me. And they have done it many years ago, yeah, but in this case only in surface layer in waveguides. Next. Yeah, this was one of the first demonstration of such a period, but very, it was not so deep, very shallow. Next. Yeah, so next. Very important work which can be done in Sony Corporation. It's such a revolution in this when people have produced a periodic structure and they produce, have a very good result with second harmonic generation, but they don't tell how the thickness of the samples. Yeah, so typically people dream about 0.5 millimeter, but they and nobody have done it, yeah, and they demonstrate good results, but don't tell about the thickness. Next, yeah, it was the results, yeah, and yeah, the thickness, next, yeah, was only 200 microns, but nobody knows about it. So in 1 year, in several groups, people produce good results in 0.5 millimeter. Yeah, it's such an interesting, you see, result, how psychology is important, yeah, for people. So it's the idea how it's possible to produce them, it's lithography, then domain engineering, which is specialized for different materials, yeah, some properties, yeah, and some other. So as a result, you have, you see stripe electrodes on one side and completely covered by solid electrodes the other side, yes. Yeah, so it's material, it's magnesium oxide doped lithium niobate, next. Yeah, and it's possible to produce such a structure. You can see that the properties of the structure is practically ideal. It's just what you see on the tops, on the polar surfaces. Yes. Next. And in the bulk, it looks, it's the cross sections. It's also perfect. Yeah, and it's about 2 microns each domain, and it comes through 1 millimeter thick. Yes, it's possible to do it. So it's also a very important demonstration. This is the theoretical result, the theoretical line and experimental results, which one-to-one correlate, which demonstrates that really the structure is really perfect. Yes? Yeah, it's possible to do it in, you see, lithium tantalite also, and in this case, the stoichiometric lithium tantalite is the best material which can be used now. So it's such a periodical pole structure. Next. Yeah, and it's possible to have a very good uniformity. Yeah, it's just demonstration of uniformity of the whole sample, practically ideal. Next. Yeah, it's application. In this case, it's years ago when people come to 15 watts. Yeah, it's very important that in this case, it's possible not to use a cavity. This device is applied out of cavity, and even in this case, it's possible to have a high energy, yeah, and very good efficiency, yes. So you can see such a result. In this case, it's above, you see, 15 watts CW. Just now, it's possible to do it above 20 watts, yeah, CW. Next. Yeah, it's different applications, and it have been done also in collaboration with, you see, famous company, you see, and it's just now they have done some devices in this area, yes. So it's, you can see here that the average energy, yeah, it's about above 20 watts, yeah, it's CW, and for pulse laser efficiency can be about 70%. You see, and it's possible to do it in all wavelengths. So wavelengths, each which you want, it's possible to produce them. Next. Yeah, then optical parametric oscillation. Next. Also in such materials, it's possible to prepare some multi-grating, and this one is very important. It's called the fan-out structures. Fan-out structure, and in this case, it's possible to move the beam, yeah, and in this case, to realize the parametric oscillation in very wide region. You see, next. Yeah, in this case, you can see it's come from 2.8 to 4.5 microns, yeah, extremely wide in one element. Yeah, next. Yeah, the efficiency is also good, it's about 20%. And it's possible to produce, wow. Yeah, yeah, next one, yeah. And it's also possible to produce it in a very wide area. Yeah, also it's possible to prepare KTP and KTR crystals. It's important that this material is just produced in, you see, in Russia, and there is still problems with lithium niobate and lithium tantalate. Yes, next. Yeah, you can see that in this material it's possible to produce it's you see solid electrodes, but nevertheless it's, you see the orientation of domains is very perfect. Yeah, because the symmetry is C2 in contrast to previous materials. Next. Yeah, and it's a periodical structure which can be done. It's next. Yeah, some demonstration what can be done with optical parametric oscillation for wavelengths 2.3. Next. Yeah, some results in this area, and the quantum efficiency about 30% in this case. Next. Yeah, it's possible to prepare some, it's new material, lithium niobate on insulator. Very, you see, the dream of people to prepare the high quality films. Yeah, next. Yeah, it's possible to prepare it by ion sliced crystalline crystals, so the perfect material, yeah, prepared on the, yeah, next. The structure of it, it's people use lithium niobate wafer, then have some helium ions implantation, and it's produced such a layer. You see, prepare the next wafer with the silicon oxide on it, yeah, next. Then some bonding of them, and it's possible by heating to have the cutting on this. So as a result, you have the lithium niobate substrate with thin film on it and the silicon oxide layer between. Next. Yeah, it's really magic. Nobody in Russia can do it, yeah, and the most famous and best results have been done in NanoLM. Yeah, it's a company in China. We have good collaboration with him, so we have such samples for free. Yeah, then next. Yeah, so it's possible to use several of them. We have the electrode under the film, we have an electrode under the silicon layer, and also it's possible to have different orientation. We have demonstrated very good second harmonic generation in all the sample situations. Yeah, you can see here the structures. You see the periods 300s, 200s, and 140 nanometers period. Yeah, stable structure. Yeah, at that time it was world record when we have done it. Yeah, so it's absolutely stable structures for many long time. Yeah, it's produced by you see by scanning probe microscopy. Yeah, it's possible to control the period and the parameters of the structure, changing the voltage. Yes, next. Yeah, it's another orientation. In this case, it's possible to produce such a domains which is just on the surface, on X-cut, yeah, on polar. And it's also by voltage it's possible to control the parameters of such a structure. Next. Yeah, also it's very interesting to produce some diffractive optical elements. Next. Yeah, in this case it's static, which people know, of course, yeah, next. Yeah, but in our case it's possible to replace the tunable one. Yeah, in this case we produce a domain structure, and without application of the field it's like a normal plate, but next application of the field due to linear electro-optical effect allows us to change the phase. Next. Yeah, and you have something like this. Yeah, so it's possible to control it and it's possible to switch it very fast. Next. Yeah, this is a variance which can be done. You see such domain structures with different orientations. Next. Yeah, it's possible to produce such a structure and some kind of you see modification of it when we change the voltage. Next. Yeah, it's possible to switch it, and you see that the switching time is below 1 microseconds in this case. Next. Yeah, it's possible to prepare some B-domain structure for mode transformation. Yeah, next. This is a result of such a mode transformation. Next. Yeah, it's a more complicated transformation when you see some two orthogonal elements. You see by two orthogonal. Next. Yeah, it's possible to produce such a new result, some angular momentum. Yeah, in this case, it's prepare the structure. This is a just domain structure which can be done. Next. Yeah, and this is the application of it when we have one element and two elements, yeah, and possible to switch them. Next. Yeah, and in principle it's possible to prepare some Sharp-Hartman sensor which allows us to demonstrate the observation and also the phase image of the same, you see, object, just switching, very fast switching. Next. Yeah, so it's just here you can see that all these ferroelectric elements much better than liquid crystals, which can be done also. And you can see that's very good transmission, very you see very robust, very good times, switching time below 1 microsecond. Yeah, element sizes. All this looks much better than what can be done before by liquid crystals. Next. Yeah, and the last one, it's very important and very new results which have been done by femtosecond laser domain engineering. Next. Yeah, this idea appears 7 years ago, yeah, in Australia. It has been done by a group of Professor Krolikovsky, yeah, and he demonstrates that by using the femtosecond laser radiation, it's possible to produce such domain structures. It has been done just in surface layers. Next. Yeah. Then it has been demonstrated that it's possible to do it, yeah, a bit later. This is a scheme of this such a cross section, and what's important is that it's possible to produce not only just near the surface but in the bulk. So you come to 3D photonic crystals. Yeah, it's quite unique possibility. Next. Yeah, you can see here which have been done, and even just now it's have been demonstrated. Several groups in the world work with it, about 2-3 groups, yeah, and demonstrated in various ferroelectrics. Yeah, and also it's possible by the same technique, next, yeah, to produce, you see the waveguides in the bulk, yeah, such depressed cladding waveguides, and it's possible next to produce them also in periodical pole structure. So it's such a dream for people for years, yeah, that it's possible to do it, yeah, and it just realized, just now I don't demonstrate our results because we have some previous results but not published yet. Next. Yeah, and this is just such a structures you see and such waveguides which have been done in the bulk and also in fan-out structures. Next. Yeah, this one is a domain structure also, yeah. Also stable one. Thank you for your attention.
Thanks. Thank you, speaker. Time to questions.
Yes.
Could you please clarify how far one can go towards reducing the dimension, the size of these periodical structures. Nowadays, technologies for nanolithography goes towards 2 to 5 nanometers and works really reliably. So you can buy chips on that.
Yeah, I can tell you that really coming to very
Can
small...
we go further towards 100 atoms?
Yeah. I can tell you that in reality, when you speak especially with the thin layers, like the thin films, it's possible to come even smaller, because in this case, they're 50 nanometers.
What is the limit?
Limit? I can tell you that
Scale.
in principle, the limit is the thickness of the domain wall. And the domain wall of ferroelectrics, it's few nanometers. Sometimes it's possible to speak about unit cell.
It's at least a few nanometers.
Yeah, and really, speaking about not such a periodical structure, but the small domains, it's possible to prepare them about 5 nanometers, 10 nanometers easily.
Thank you.
Yeah,
And
I
short
can do it.
related question. If you make it three-dimensional, I mean these
I see.
elements, for example, slopes, you could just rotating them vary the wavelengths that they are produced, or something like that.
No. Typically, it's oriented just along the polar X, and it's not stabilized. It's like small, short lines. But in this case, the sizes it's about microns. When you speak in the bulk, but it's only the first steps. I hope that it's possible to do it. And speaking about, you see the smallest sizes is just. In ferroelectrics, it's much better than in ferromagnets, for example, because the thickness of the wall is extremely small. Yeah, you're welcome.
Unfortunately, we have a limit of time, and let's say, speaker.
One word, I can tell you also that this is the emblem of our company, and we are the only company in Russia who have produced such an elements. So it's not only, you see, ideas, not only science, but also the applications for all of them can be, you see, and we can prepare especially for you for special parameters which you need. Yeah, thank you.
Okay. Let's thank speaker again. Next talk will be presented Dr. Guriev, two-mode lasing in disc lasers with degenerated configuration cavity.
Не работает, да? Господи, thank you for introducing me. First of all, I want to say that I'm glad to present my talk here today. And my talk will be about two-mode lasing in disc laser with degenerated configuration cavity. Next slide, please. Here you can see outline of my presentation. First of all, I will say about motivation of this work. Then I will touch previous works of our scientific group. And then I'll say a few words about difference between previous work and current work. And then I'll demonstrate all results that we obtained in this presentation. And in the end, I will say a few words in conclusion. Okay, the motivation of this work is that stable dual frequency lasers with narrow line with sub-gigahertz difference frequency is applicable in different spheres of science and technique. For example, radiophotonics, interferometry, laser spectroscopy, and metrology. And usually such lasers that operates in dual frequency regime use in the cavities some spectral and special selectors. And because of this, the design of these devices is becomes complicated. Also, this problem, creating of stable dual frequency lasers, can be solved by using of lasers with degenerated cavities. It is widely known that degenerated cavities has its own spectral selective properties. Can you? Okay. As I said earlier, and Vladimir Borisovich said earlier, that our group had some works in this sphere of disc lasers with degenerated cavities. And previously was demonstrated that disc lasers can operate in dual frequency regime. Oh, sorry. Previous slide, please. Oh, thank you. So in this work was shown that disc laser can operate in dual frequency regime. And also was shown that disc lasers with degenerated cavities can operate in single frequency regime. By means of these two works, we can conclude that degenerated cavities had its own spectral selective properties. And also I must note that these two works, in these two works, lasers was operated in fundamental transfer mode operation. Next slide. And in the current work, we decided to increase pump spots on the disc. And so we could to excite transfers modes of higher order. So on this slide you can see a scheme of degenerated cavity that was used in this work. Here is we used a disc of E3 orthovanadate with neodymium ions with this thickness. And on the back surface of this disc was deposited a high reflective coating, which was the flat mirror of our cavity. The second mirror of our cavity was a spherical mirror with a radius of curvature about 200 millimeters. And this mirror has two zones with different reflective coatings. This part of the mirror had a reflective coefficient equal to 90%, and this zone of the mirror was high reflective for lasing wavelength. So we use 3 pump spots in this scheme. So using of 3 pump spots can provide such trajectory of lasing radiation. You can see that it looks like M letter. So this scheme can be called as a degenerate M-type cavity. But to prevent the lasing along this axis because of this pump spot, we deposited a non-transparent screen on this axis, so here on this image. Well, Next slide, please. So here you can see the setup scheme, no, experimental setup scheme, where we could study all the properties of lasing radiation. For example, energy properties, temporal, spectral, and spatial. Next slide, please. First of all, we study the temporal characteristics of the lasing radiation, and this study we carried out due to fast photodetector and oscilloscope with a bandwidth of 4 gigahertz. So here we can see a waveform of lasing radiation, which corresponds to waveform of beating of two modes with frequency of 360 megahertz. And also here we can see that this mode beating is staying stable in the scale of milliseconds. The study of radio frequency spectrum show us that this waveform has only one frequency, that was 360 megahertz, and here we can see that this peak is very narrow, and it has width about 3 dB on the full width half maximum, and this peak corresponds to resolution of our radio frequency spectral analyzer. Next slide, please. Thank you. Also, we carry out study of spectrum of laser radiation, and this study we carried out with interferometer Fabry-Perot with 40 millimeter base length. And here you can see interference pattern of laser radiation, and this pattern corresponds to two spectral components. You can see it here. It is one more proof of existence of only two modes in laser radiation. But also we must understand what are these two modes, because in previous work was shown that for our cavity, the intermode interval for longitudinal modes must be about 1500 megahertz. But in our case, we obtained modes beating with frequency 360 megahertz. So if we use some equations for frequencies of modes of Hermite-Gaussian modes for degenerated cavity, so we could understand that we have here two transverse modes, and these modes are adjusted between them. Well, and next slide. So we must to prove that we really saw operating in two transfer mode regime. And so we perform a divergence analysis of laser radiation, and it showed that divergence of radiation along the horizontal axis is bigger than along the vertical axis, and so we can conclude that radiation distribution corresponds to multimode radiation. Next slide. And now I can finish my talk, and in conclusion I want to say that two-frequency lasing was obtained in a disk laser with a two-mirror generated laser cavity with M-type with M configuration of the intercavity of axis ray path. The dual frequency was realized due to the intrinsic spectral selective properties of the degenerate cavity without the use of additional optical elements. And the intermode bit frequency was 360 megahertz. That is all. Thank you.
Thank you, speaker. We have a minute for questions, please.
I have a short question related to disk laser. If one would think of increasing the power of this system, he or she could think of replacing this tablet use with the tablet of random laser. How it used for random lasers. So fabricate for random lasers. What will happen with your production of laser radiation in this case if you replace just crystal with random laser?
Okay, can you please repeat your question?
Just replace. You use a crystal plate. If you need to increase the power of production of laser radiation with the system, you would think of replacing this crystal with random laser. You know what is random laser?
What? Please.
Random laser.
Random. Oh, okay. Mm-hmm.
What will happen? Does it work?
I can say that we just research laser operation in small power levels, and I can say that we have no opportunity to use big pump power. So I can't say what would be in this case yet. I hope I answer your question.
Okay, thanks all. Thank you very much. Let's say, speaker, thanks again. And, I have a question to organizer. What about online connection? Нет, да? Okay, unfortunately, next speaker could not connect with our due to the problem in the internet. I don't know why. So now it's a coffee break, and maybe this speaker will present your talk in the next section. Yeah. Okay, thank you very much.
разрушение энергии срывается в такой режим, что жопа не находится. Вот эти вот филаменты, значит, они там вот, ну, собственно, что такое типа проживание получается в дневной области. Ну, сомнительно. Дальше, ну, это вроде как вот все играет, короче, психологические отношения. Если это делать с энергией, насколько я сейчас понимаю, насколько он даже делается, одновременно, как есть еще и переключение. Просто переключить достаточно трудно, ну и просто какой-то режим, там еще просто переключение. Но когда они уже ставят филамент, они все через чтобы не перепутать, что условия как это сейчас выглядит, это короткая полоса. В смысле, стерженьки. Это вообще значительным количеством будет готово. Поскольку до сих пор вообще очень ничего похожего не делали, поскольку все как исследования, которые стало, просто очень что на этом можно делать. Ну, плюс, значит, конечно, вот это, да, значит, БРБ, который рисует полосочку. Да.
Okay, dear colleagues, it's time to start a session devoted to laser diagnostics and spectroscopy 2.1, the first part of this session. And we should have two talks, but as I understand, there will be only one talk in this session. The first one by Sergei Aseyev from Institute of Spectroscopy, Russian Academy of Science. And you see the title, please.
Good afternoon, dear colleagues. In this talk, I will speak about the current state of the experimental activity in the field of ultrafast electron diffraction and microscopy in our country. Here I will speak about the detection of ultrafast processes. Basically, this is a pump-probe approach, where the pulse laser initiates the dynamics in the sample, and the electron pulses probing this structural dynamics. The global purpose of this project is to detect atomic motions with electrons. In other words, to observe structural dynamics in four-dimensional time-spatial continuum. Comparing electrons with X-ray, with which it's possible to reach high spatial resolution in combination with high temporal resolution, we can compare this characteristic according to this simple table. We can say that effect of X-ray on the sample is more destructive, while for electron approach, we need high quality, very thin, spatially homogeneous sample. This is an exciting example of the solid to liquid transition in semi-metal initiated by femtosecond laser. And you can see how the diffraction pattern changed dramatically in only a half of picosecond time. Strictly speaking, the base of the ultrafast electron diffraction is those three experimental ways: diffractometer or electron microscopy, femtosecond laser techniques, and of course nanotechnology in order to produce high quality samples. Ultrafast electron diffraction can be relativistic ultrafast electron diffraction in order to grab very small size of the electron burst, ultrafast electron diffraction with radio frequency electron pulse compression, and using a compact electron diffraction apparatus. We used the third approach. Here is depicted tabletop apparatus for ultrafast electron diffraction, which is in the Institute of Spectroscopy in Troitsk. Here's the photo of this. It's a very compact device. Two channels. Pumping from Tysify laser illuminates the sample. Here, as you can see, the sketch of this setup, while the probing pulse obtained by illumination of the third harmonic of silver cathode produced a burst of electrons, and these electrons are using as a probing for this process initiated in this sample. In order to produce very short electron pulses, we need, in this approach, we need very small gap between the cathode and the sample. It's only 1 centimeter. The first thing is a special temporary overlapping of light and electron pulses. Even here, I gave the quote from an article of the authoritative scientist Dwight Miller, who has worked in Canada and in Germany. Here we produced a very dense electron cloud illuminating the gold mesh by strong femtosecond laser. And we observed the scattering of the electron burst which passes through the cloud. And with this approach, we can determine the time zero position with accuracy of 1 picosecond. So this is illustrated by this picture. Comparing to the destructive melting of bismuth, here I will speak about non-destructive solid-to-solid transition in semimetals. Two pendulums in the hand illustrate two mechanisms of coherent phonons in these compounds, where it is rather simple to generate phonons using by moderate femtosecond laser pulses. Here, this is example. If, for example, we are using pump laser with power density of about 7 millijoule per square centimeters, we produced force about 5 times 10 to the minus 12 Newton. This force can be compared with the interaction between two elementary charges separated by 1 angstrom. It's 10 to the minus 8 newtons. And if we speak about this value, millijoule per square centimeters, we can illustrate that this value is approximately 1 eV or square angstrom. Detection of phonons by ultrafast electron diffraction is as follows. So we have the samples, the crystal samples with very thin crystals of antimony or bismuth fields formed by or using thermal deposition technique on a carbon substrate, which is applied in classical transmission electron microscopy. We illuminate these samples by femtosecond laser pulses, and with different delays, we probed these processes inside the objects of investigations. We can see oscillations more details are given in the following slide. So you can see the oscillations of the electron diffraction signal as a function of delay between the laser pumping and electron probing. After Fourier transform, we get the characteristic frequency oscillations of the signal. And we can assume different oscillations modes. And this mode, the second harmonic of E1J mode, is the new one, which was not previously detected. The situation with bismuth is quite more interesting. This compound has extremely huge, the Fermi wavelength is about 30, 40 nanometers. So it's possible to detect quantum confinement in very thin films, which is assumed to the high density of photo-generated carriers confined within a thinner films. And for illustration, you can see this pressure cooker. So the oscillations with a large amplitude are accompanied by anharmonicity. This is a calculation of potential energy surface for different electronic temperature inside the sample. And here the large scale amplitudes. We detect, for the first time, we detect the third harmonic of A1J mode inside thin bismuth fields. Because no data are available in the literature on the duration of the third harmonic inside this compound, we can assume that our results are likely to be related to the manifestation of quantum confinement in bismuth. As I told previously, the nanotechnology is very crucial for this approach, because for experiment we need extremely thin, extremely high quality samples for ultrafast electron diffraction. And here you try to see to what extent it is possible to use graphene substrate for this technique, for developing of this approach, because we need some substrate in order to produce very thin films for the experiments. And here we discovered that the time of light, the time of life of the graphene layer is quite about 3-4 hours if we use typical experimental conditions. And what it means, the brightness of the electrons from graphene decreased twofold, which was caused by breaking of carbon bonds. Also, we can see the appearance of new diffraction rings, which corresponds to the new material. Here, before laser experiment and after the laser experiments, negative and positive images. And the conversion time of the frames, 1 second for this pattern, while 3 seconds for this. We discovered that structural modification of graphene on a copper grid in a strong laser field was connection with the formation of copper oxide, and another oxide of the copper. The copper oxide could be formed in the presence of residual oxygen inside the vacuum apparatus. And here we compare the theory and experiment from which we can detect the sample composition after this alpha laser experiment. It means that typically this graphene layer is good, but only good during 3-4 hours. After this, you can change this to another. You should change to another sample. Future topics, this will be connected with the study of phase-change materials. Almost all of us maybe remember the very famous article from Stanford University in PIL many years ago, reversible electrical switching phenomena in disordered structures. To set a memory cell amorphous phase-change materials undergoes crystallization. For research, crystalline phase-change materials is first melted, and then the liquid is rapidly quenched, accompanying the amorphization processes. This type of materials are used for memory applications, and Raman and X-ray measurements on germanium telluride films are planned to be supplemented by ultrafast electron diffraction. It's very interesting that this confinement effect, which is equal to competition of electron localization and electron delocalizations, can be illustrated by thick book where the distance between the adjacent pages are equal, and the thin book when the periodicity is violated. It's interesting also that this effect is only for crystalline, while for amorphous phase is not described. Our ultrafast electron diffractometer is used only for electron diffraction mode. And in order to develop ultrafast electron microscopy, which can be worked also in ultrafast electron microscopy mode, in imaging mode, we modified Hitachi H300 transmission electron microscope, and it has been successfully modified to allow for both optical sample excitation, which is given by this picture, and pulsed electron emission, which is given by this picture. Yeah. Here we see the images of hole inside, nanohole inside aluminum, and diffraction patterns of this picture on aluminum nanoparticles obtained in two modes: usual continuous mode and thermionic mode. And when we used pulsed electron beams, here we also see the interaction of electron clouds formed near these wires with the ultrafast electron pulses. This approach helps us to solve T0 problems and to find T0 for these apparatus. With femtosecond lasers, if probing pulses with a small number of electrons in the limit single electron wave packets are used, the stroboscopic regime enables ultra-high spatial temporal resolution to be obtained, which is not restricted by the Coulomb repulsion of electrons. In the limiting case, a 4D microscopy actually operates with single electrons wave package by their correct description, unlike that of multi-electron wave packets, encounters with zero difficulty. A humorous story from a letter from Israeli professor to Vladimir Vinogin. At the exam, the professor asked the student, "What is an electron?" "You see, professor, I remembered it this morning, but now I forgot it." "Young man, you must definitely remember it because you are the only person who knows what an electron is." And here's acknowledgements to our colleagues, and this is also cover pages of recently published book in Moscow. Thank you very much for your attention.
Thank you. We have time for questions, please. Yeah, sure.
What you have talked about is extremely exciting, and I would just the question related to even more excitement. What would happen if you use an additional probe, for example, X-ray radiation or terahertz radiation? X-ray, as I know, was a dream. X-ray, optical, and electron beam was a dream of Ahmed Zewail. To make a probe that will make picture snaps of what is going on with the matter with a time resolution of something like few femtoseconds. Yes. And what new would add X-ray and terahertz radiation?
Thank you for your nice question. In principle, there is approach when different techniques are combined on the one apparatus. For example, in Canada, the Civic, when he merged two techniques, terahertz technique and electron probing on the same apparatus, he obtained additional information. He can follow not only the structure of this compound, but also the very thin features of the vanadium dioxide. He can tell about that the structure, the change in the structure in the vanadium dioxide can occur without, the question, yes, is very useful technique, is very crucial technique, but what precisely characteristic of the sample you can measure with terahertz pulse, I don't remember, but it's definitely what's used. And
terahertz, for example, extremely well fit, very small in biological molecules, or in explosives. So it really fits to the structure of molecules, and can be useful for that. If structure changes during time, this would bring additional information.
For example, in these phase change materials, they combined, and they also combine optical approach and electron pulse approach in order to see that their transmissions was changed, optical transmission was changed, but the structure was not changed, and vice versa.
Are there any experimental works around the world on that? I mean, combining optics and X-ray, optics and terahertz?
Optics and X-ray, I don't remember, but optics and electron pulse, I know about a few experiments in Germany. Terahertz and X-ray, terahertz and electron pulse was done in Canada. It is a guy who was the PhD student of Dwight Miller Civic. Now he has a group, his own group, and they did a lot of vanadium dioxide. This vanadium dioxide was first initiated by Zewail. It was a very controversial article. Then it was continued by Civic. It was extremely difficult experiment, more one day. You need scan. And also in this approach, I remember that it was used terahertz pulse. In the same machine, but I don't correctly remember the details of terahertz.
And as far as I know, Miller returned back to Canada from Germany.
Dwight Miller, yeah.
And he continues this.
To try to work in this field.
Okay, other questions? Well, if not, let us thank the speaker again. Thank you.
Thank you.
The second talk should be online, but there's still no connections, so we have no other talks. That's all for today. And the next session will start at 2 p.m. after lunch. Thank you.
Уважаемые коллеги, есть предложение начать очередную сессию секции лазерной диагностики спектроскопии. И colleagues, we started next session. Ну ладно. Dear colleagues, we start next session of our laser diagnosis and spectroscopy section of the conference. And the first talk in this session will be delivered by Professor Alexey Kalachov, who represents the Federal Research Center in Kazan, Tatarstan Republic. And the title of the talk, which reflects his own interest in science, is named Promising Schemes of Heralded Single Photons Qubit Sources. You have 20 minutes ahead.
Thank you, Victor, for introduction. And first of all, I would like to thank organizers for inviting me, and it's my great pleasure to be here. And in this talk, I'm going to discuss single photon sources, which are based on optical nonlinear effects such as spontaneous parametric down conversion, spontaneous full wave mixing. And I would like to present some promising schemes of heralded sources that allow us to generate single photon qubits with the highest possible heralding efficiency. Oops. Thank you. So it's well known that single photon sources have become essential for the implementation of optical quantum technologies such as quantum communications, quantum computing, quantum metrology. And usually we are interested in single photons, correlated photon pairs, and more complicated quantum states of light. And in this talk I will focus on single photons which are used as flying qubits, probably the most important resource in quantum communications and optical quantum technologies. To be more precise, it should be noted that when we are talking about single photons, we actually mean single photon wave packets, a superposition of photon number states with different frequencies and different wave vectors, so that we deal with single photon optical pulses limited in time by coherence volume or in time by coherence time and in space by coherence volume. And in this context, pure single photon states, which are very important for optical quantum computing, for example, corresponds to transform limited single photon pulses. And in more general case, such pulses may be a superposition of two ones corresponding to orthogonal modes or orthogonal states of the electromagnetic field. And for encoding of quantum information, we can use various degrees of freedom, for example, polarization, time, frequency, also spatial structure of light beams. All of these encodings are of interest for optical quantum technologies. And a natural way to emit single photons, to produce single photons, is a spontaneous emission of a single quantum emitter like quantum dot, single atom. And there are several the main advantages of this approach are producing of single photons on demand and the absence of multi-photon contribution in the resulting field. However, there are also some disadvantages and technical problems. First of all, to produce pure single photons, we have to cool these devices down to liquid helium temperatures. Also, it's difficult to combine high extraction efficiency and high spectral purity in a single device. And it's difficult to tune such sources and frequency, and usually to produce identical sources, a series of identical sources. Therefore, another approach, which is based on optical nonlinear effects, is also interesting, promising, and is also a topic of active research. For example, spontaneous parametric down conversion, which is observed in second-order nonlinear materials, has been widely used as a source of correlated photon pairs. And in such a case, we can generate various types of entanglement, for example, frequency entangled photon pairs, as shown here, which is described basically by this two-photon amplitude of the biphoton field. In addition, the photon number correlation between the resulting fields allows us to herald the existence of one photon by detection of its pattern. In such a way, we obtain so-called heralded single photon sources. And such sources can be designed to produce pure single photons at room temperature. They are readily integrable and then also can easily be tuned in frequency. And of course, the same results, the same class of states can also be obtained via spontaneous four-way mixing, which is observed in third-order nonlinear materials. And in this talk, I would like to present two groups of results. The first one is related to producing single photon qubits in so-called photonic molecules. This is systems of coupled micro-ring resonators, and these sources are based on spontaneous four-way mixing usually in such systems. And the second group of results are related to producing spatial or temporal time bin or spatial bin qubits via spontaneous parametric down conversion when states with orbital angular momentum is used as basis states for qubits. So the first question which I would like to discuss is how to generate pure single photon states in a system of micro-ring resonators. We consider micro-ring resonators for several reasons. First, efficiency of nonlinear optical effects in such systems may be high due to small mode volume and high quality factor of micro-ring resonators. And this results in significantly reducing required pump power. High free spectral range may be due to small size of such resonators and simplifies frequency demultiplexing and filtering of the pump field. The bandwidth of the emitted photons may be small enough so that such fields become compatible with quantum memory devices based on atomic transitions. And finally, CMOS compatible manufacturing process allows us to embed such micro-rings in photonic chips. And in such a way, we can approach near deterministic generation using spatial multiplexing in these systems. Here are some examples illustrating these advantages. So high rate generation at a low pump field, low power of the pump field, small bandwidths of the emitted photons. And third result illustrates that we can produce single photons with a purity above 90%, in this experiment 92%. And it should be, of course, it's interesting that this value is close to the maximum value of purity, which can be obtained in a simple micro-rings without special design. So it is interesting to discuss, is it possible to produce single photons with a purity close to 100%? And we consider the following, please switch, thank you. The following system of micro-ring resonators, which may be called as photonic molecular. Spontaneous four-way mixing occurs in the central micro-ring, and other micro-rings are used for resonant coupling between this one and straight waveguides. So one resonant coupling is used for loading the pump field, and two others are used for unloading idle and signal field. It is possible to design this system so that idle and signal fields propagate in different waveguides without the pump field. So we can implement frequency demultiplexing simultaneously with producing correlated photon pairs. And the main parameters here are coupling constants between microrings, which are denoted here by G, and constants between coupling constants between microrings and straight waveguides, which are denoted here by kappa. And it is important that in this system we can tune these parameters independently, and thereby we can optimize the system for producing pure single photons. In particular, we found optimal ratios between these parameters for the pump field, for the signal and idle fields, which provide the largest area, the largest region corresponding to zero group velocity dispersion around the center frequency of the resonant lines. And this is important also for avoiding distortion of single photons in this system and to achieve pure single photon states at the output. The main characteristics of generated biphoton field is so-called joint spectral amplitude, which is the probability amplitude of emission signal and idle photons at some specific frequencies. And to analyze frequency correlation between the photons, we can take advantage of well-known Schmidt decomposition of this function, calculate the Schmidt number, which is noted here by K, capital K, and purity of heralded single photons, which is calculated as 1 over K. So if Schmidt number is equal to 1, we have factorable joint spectral amplitude and pure single photons. And our aim is to approach this regime. And the main result of numerical simulations and optimization is shown here. The left figure corresponds to the usual case without special design when we have, for example, one microring resonator. In this case, line width for the pump field is equal to that of for the signal and idle fields, and you see that there's still some correlation between frequency correlation between the emitted photons. So the horizontal axis corresponding to idle frequency, this axis for signal frequency. So the resultant purity is about 94–95%, which slightly depends on the material, but anyway we have some upper limit without special design. And the right figure corresponds to the case when we made line width for the pump field much larger than that for the idle and signal fields, when we use optimal ratios between coupling constants, which I mentioned before, and when we apply optimal spectral widths of the Gaussian pump pulses. And in this case, we have purity very close to 1. So the conclusion is that photonic molecules, a system of microring resonators, allow optimization in such a way that we can produce almost pure single photons. And in such a system, now let us consider how to generate frequency bin qubits. To produce frequency bin qubits from a single frequency pulse, we can take advantage of electro-optical modulators and Fourier transform pulse shapers, and this device is actually equivalent to implementation of single qubit gate in frequency domain. For example, we can place such a device at the output of our heralded single photon source, which operates under receiving some heralded signal. The problem is that heralding efficiency in this case. What is heralding efficiency? This is a probability of observing frequency bin qubit at the output of our device when heralded detector signals receiving of the idle photon. So the heralding efficiency is reduced by insertion losses of this system and also by the less than unit success probability of such a gate. And therefore we suggested another approach. We use a similar device. We apply it to the pump field before spontaneous four-way mixing. And in this case, under appropriate manipulating by the pump field and under appropriate detection of one of these photons, we can transfer the state of the pump field to the state of the signal field. And in such a way, we can produce frequency bin qubits with the highest possible Heraldian efficiency because no additional devices are here. And for this end, we can resort to single or strong coupling regime when each resonant mode is split into a doublet. And such doublets, such splitting can be used for preparing narrow band single photons compatible with quantum memory devices, for example. And the splitting of the resonant lines results in 4 peaks of joint spectral amplitude. Instead one peak, we have 4 ones corresponding to different combinations of frequencies. So both photons have small frequencies, both photons have large frequencies, and the middle group corresponds to the case when one photon has small frequency and another one has large frequency. If the pump field is broad enough, then we excite all these peaks in the biphoton field. But we can adjust the pump field so that excite only part of them. For example, we can consider double frequency pump field, which is 2 components shown here by the dashed line, and excite only 3 peaks shown here. And when we detect heralded photon only with high frequency, then the state of the resulting photons is a superposition of 2 frequency components, and what is most important in that amplitudes between these components, relative phases and amplitudes, are completely determined by the pump field. To be more precise, they are squares of the corresponding amplitudes in the spectrum of the pump field. So we can produce frequency bin qubits with the highest possible efficiency when the state of the qubit is completely determined by the spectral amplitude of the pump field. And also the resulting state doesn't depend on the mode of the resonator mode frequency, which makes it possible to use frequency multiplexing in order to increase the rate of generation of such frequency bin qubits. And now let me to the next part, second part of my talk related to temporal and spatial bin qubits, and this task is closely related to the pulse shaping, heralded single photon pulse shaping in spontaneous parametric down conversion, for example. The idea of how to manipulate pulse shapes by controlling pump field has been developed more than 10 years ago for the time domain and for the spatial domain. And I would like to focus on the second one. In this case, the spatial structure of the heralded photon can reproduce the spatial structure of the pump field if one of these photons, the second photon, is detected in the simple plane wave mode. And in such a way, we also can reproduce special qubits by manipulating the pump field with the highest possible efficiency. An interesting variant when we use states with orbital angular momentum, which are an important resource in quantum communications. In this case, when we have in the regime of longitudinal collinear spontaneous four-way mixing, we have the following conservation law. So the momentum of the pump field is equal to sum momentum of the idle and signal field. And if one of them is detected in the mode with 0 orbital angular momentum, then momentum of the second field is equal to that of the pump field. In such a way, if you prepare some superposition of orbital angular momentum in the pump field, we can transfer this superposition to the heralded photon. And actually, this is the same approach as was discussed in the frequency domain. And using this approach, we implemented quantum hashing with quantum bits, with qubits based on orbital angular momentum state. So in this case, we prepare the following, we use the following states of special qubits based on on pairs with opposite orbital angular momentum with equal weights and different relative phases. This is useful because such a state allow us to avoid distortion due to GUI phase while photons propagate in free space. And according to our measurements, quantum tomography measurements, we managed to prepare and to control such states with accuracy in phase about pi over 256, which allow us to prepare quantum hash functions consisted of several qubits, up to eight qubits. Okay, and the idea of quantum hashing is formally quite simple. We have to map a classical input state consisted of several.
Time, unfortunately.
I'm already close to the end. So several bits, classical bits, to quantum message consisted of several qubits, so that we can able to compare large classical messages by using small quantum messages. And main requirements to this mapping function is resistance to inversion and resistance to quantum collisions. And shortly speaking, we check properties, basic properties of quantum hashing for different number of qubits when we encoded quantum classical message consisted of 9 bits. And we obtain a good agreement between theory and experiment for different values of orbital angular momentum, which means that we can use multiplexing, spatial multiplexing, to increase the rate of preparing and analyzing such quantum hash functions. Okay, so let me come. This is conclusion. Basic results, basic papers, and just to mention my colleagues, which my co-authors of this work. Thank you.
And we have a short time for a couple of questions.
Thanks, very exciting talk. And if we go back to this scheme with 4 rings, how do you avoid the longest wavelengths to couple to all 3?
Sorry, go back to the scheme with 4 peaks?
4 rings. The
main ring
rings. And the other 3 which couple pump, idler, and the signal. So the idler will probably fit to all 3 because it has longer wavelengths.
In frequency domain, I would like to show this picture. So if we choose the length of the smaller rings, for example, 3 times smaller than that of the central microring, then we have the following picture in frequency domain. So this is free spectral range for central ring, and for other rings for resonant coupling we have 3 times larger free spectral interval.
I mean in real life. In
real life, yeah, we can.
When you have some distortions and so on.
You mean non-equidistant spectrum of this microresonators?
Well, this is not the short question. So
yeah, it's in real life. We estimated how to produce such a system in real life. Of course, it's not a simple task. We have to tune these microrings with high accuracy in length, and we simulate this for microrings based on silicon nitrogen. And in principle, in this case, we obtain a comb structure consisted of about 40 modes. So it's promising for implementing and even for multiplexing, frequency multiplexing. I mean, silicon nitrogen microrings are promising material for that. Okay, thank you.
And second and last question.
Very short question, thank you very much, Alexei. When you speak about generation of entangled photons, what's the real bandwidth of your source? I mean, in nanometers, is it possible to say? And how broad it can be done?
It depends on the system. You can see that if you use just crystals, then of course spectral width may be nanometers, tens nanometers, and even more. So the largest bandwidth obtained in SPDC regime is, as I remember, about 300 nanometers.
When you spoke about broadband regime, what's wrong with broadband regime? Because in your presentation it's non-modest.
Broadband regime. Well, in the case of cavity, microrings or other types of cavity, of course, they aim to obtain narrowband photons, not broadband. So broadband may be obtained without cavity. In this case, we have at least several nanometers and more. In the case of cavity-based systems, our aim in typical is to generate gigahertz photons and megahertz photons. So the smallest spectral width is sub-megahertz in such a system. Typically, in microring resonators with good quality factor, we can obtain megahertz bandwidths of photons.
Okay. Thank you, Alexei, for your talk again. We have to go further. According to our program, the next invited talk in our program will be given by Dr. Ilechin. And the title of the talk is Near-Field Optical and Infrared Spectroscopies of Semiconductor Nanostructures. And he will present a team of people headed by Ржанов Institute of Semiconductor Physics in Novosibirsk, Russia.
Good afternoon, everyone. Thank you very much, Mr. Chairman, for your kind introduction. First of all, I would like to thank the organizing committee for inviting me to present the results of our work here in such prestigious conference. And this work has been appeared as a result of cooperation between four institutes. Actually, it's a Zhanov Institute of Semiconductor Physics, and three universities from Novosibirsk, Moscow, and Technical University of Chemnitz. My talk will be organized as the following. In the beginning of my talk, I will give short introduction and motivation. Then I will present our results regarding tip-enhanced Raman scattering and nano-IR spectroscopy by aluminum nitride nanocolumns and hexagons. And then I will show our results devoted to tip-enhanced photoluminescence from D-chalcohenides, metal chalcohenides like molybdenum disulfide and tungsten disulfide monolayers. And finally, I will speak about so-called gap mode tears. I will speak a bit later by cadmium selenide nanocrystal monolayers, cadmium selenide cadmium sulfide co-shelled nanoplatelets, and multigraphene. And at the end of my talk, I will give conclusions. So, of course, well known that optical spectroscopy, including Raman scattering, photoluminescence, and infrared spectroscopy, are widely used for determination of small amount of matter down to single molecules, and they found application in various fields of science as well as in medicine. But I'm working in the Institute of Semiconductor Physics, therefore I'm interested first of all in properties of nanocrystals, nanowires, nanocolumns, two-dimensional and one-dimensional materials, etc. because they possess new electronic, optical, and phonon properties, and also they found a wide range of application in, so for example, light-emitting diodes, photodetectors, memory devices, etc. We just heard yesterday from plenary talk of Professor Andrei Naumov that significant progress have been achieved for photoluminescence measurements of single nanostructures. However, the study of the electronic properties is still on demand. However, Raman and infrared experiments with single nanostructure remain quite rare, since they're dealing with ensemble of nanostructures, while the data on phonons and single nanostructure remains in general unknown. Therefore, this is because of extremely low cross-section from Raman scattering in single nanostructure, which prevents the determination of its phonon spectrum. Therefore, our motivation was to elaborate approaches for plasmon enhancement of optical response by semiconductor nanocrystal ensemble, going actually towards the observation of optical response in single nanocrystals. Let's speak about experimental realization of so-called tip-enhanced Raman scattering, and simultaneously we can measure also tip-enhanced photoluminescence. In general, experimental realization of this equipment looks quite simple. Through the optical objective, light from the laser enters the very tip of metallized atomic force microscopy cantilever and excite the surface plasmon at the edge, at the tip of such cantilevers. If nano object is located in the vicinity of this cantilever, then it's located in this high local plasmonic electromagnetic field induced by plasmon and Raman enhancement of Raman scattering in proportional, in this case, 4 order of this electromagnetic field. So it means if we able to enhance electromagnetic fields near the tip apex by a factor of 10, we received enhancement in Raman scattering 10,000. So, and we use in our experiments Haribo Explorer Nano device, which is recently installed in Novosibirsk. The important input which we expect from tip-enhanced Raman scattering and tip-enhanced photoluminescence are the following: that we are able to observe single nano object, then we can see strong enhancement by Raman scattering in PL signal, which allows to investigate the details of electronic and phonon spectra. We are able to perform mapping with nanometer spatial resolution and obtain also high spectral resolution. Okay. Nano IR spectroscopy works a little bit different. It used infrared spectrometer combined with IFM microscope, and the heart of the spectrometers is actually Michelson interferometer. In one of the arm, such cantilever is installed, and infrared light illuminate the cantilever. Cantilever is vibrating with some particular frequency, and the signal is detected in so-called heterodyne modes, and therefore we can just see the scattering by light from the beneath of the tip of cantilever. So for that experiments we have used near-spec infrared spectrometer. So the heart of the TERS experiments is TERS tips for that, or cantilevers. So actually in our experiments we have used commercial atomic force microscopy tips, which are shown here. We bought it from the TIPS Nano company, And the tip apex looks like that from initial tip. Then we can deposit metal, either silver or gold, on the surface of such cantilevers. And it allows us to very plasmonic energy. In addition, we are able to deposit silicon dioxide. It gives us additional freedom in varying plasma frequency. Okay, and here I would like to switch to results, and here we investigate so-called aluminum nitride nanocolumns, which is shown here. The diameter of nanocolumns is about 200 nanometers, and it's located on the silicon substrate covered by gold. If we measure standard tierce spectra, we can see in the optical spectral range of aluminum nitride phonons that some new features quite strong appears in the range between transverse and longitudinal phonons of aluminum nitride. And this feature was attributed to so-called surface optical phonons. If we monitor intensity of these modes, we can obtain the mapping of this nanocolumn. Important here is if we change the polarization. Typically, all tierce experiments are made in this geometry when the light is polarized along the tip apex. However, if we just change polarization along perpendicular to the tip axis, we can see the strong enhancement from the edges of nanostructure. I would like to pay this attention that it can happen just only for this well-developed structure when their size is comparable with the tip apex radius. Okay, we have investigated aluminum nitride hexagon shown here. It was grown on aluminum nitride layer, so everywhere here is aluminum nitride layers, and the height of this hexagon is 30 nanometers. Again, in Raman spectra, we can see the features attributed to surface optical phonons. If we plot intensity of these features as a function of distance, we can obtain very similar images which we can see from atomic force microscopy experiments. Even more detailed information can be obtained from the nano-IR imaging of the same hexagon. We can go through, by the tip, through this cluster like shown here, and we can see several modes actually which change the frequency position as a function of the spatial position. And the main conclusion is that we can see several phonon modes like shown here, and important is if we try to monitor intensity of these modes, we can see different localization of these modes on the surface. For example, low frequency modes is localized at the edges of such hexagon. This mode is located over the whole surface of hexagon, and this mode is belong to two-dimensional aluminum nitride layers. Okay, now I would like to switch to tip-enhanced photoluminescence results on chalcogonide monolayers with a thickness about 3 monolayers. Here we can see triangular island which is gradually increased. For example, this area is shown here, and we can see some defects here. What happens in photoluminescence spectra actually? So we can see photoluminescence with maximum. So this is first of all exciton luminescence in tungsten diselenide, and intensity is distributed like shown here. The frequency position or peak position map is presented here. We can see the variation in position of photoluminescence maxima at the defects of the structure. So I would like to pay here attention that we have used 532 nanometers, but we received the spatial resolution much below diffraction limit. So, okay, these very similar results were obtained for molybdenum disulfide monolayers. Here I just show IFM images in comparison with TER images results. Here I show just only age of this structure, and finally we can see even the very age of this structure, and still we can see even, we can reach even resolution with optical method like 50 nanometers like shown here. And here the spectra, photoluminescence spectra are shown. Now I would like to say a few words about gap mode TERS experiments. So it works when the metallized atomic force microscopy tip is contacted to so-called plasmonic structure. In our case, this is array of gold nanodisk. And if our object can be either nanocrystals or nanoplatelets is located between these two metal nanostructures, then the strong enhancement of electromagnetic fields is achieved, and therefore we can get ultimate Raman enhancement. Okay, so we know actually everything about our gold arrays of nanodisk. We know the energy position of plasmon in this structure. So therefore now we can switch to experiments on such nanodisk. We have chosen particular structure with some particular size. Okay, and here we deposited on such structure just only one monolayer of cadmium selenide nanocrystals with the size of 6 nanometers. They're distributed everywhere here, but we cannot see them with such a scale. Okay, but if we measure Raman signal from area at the edges of such gold nanostructure and away from this, we can see different Raman spectra, which are actually, these features comes from longitudinal optical phonons and their overtones and cadmium selenide nanocrystals. And if we follow into the intensity of these modes, we can make mapping, and we can see that the main Raman signal comes predominantly from the edges of such nanostructure. So we did similar experiments with core-shell nanoplatelets. They distributed over the plasmonic structure like shown in IFM microscopy or scanning electron microscopy images. And in TERS experiments, we can see some areas which are located close to plasmonic structure. If we zoom in the structure and repeat experiments, we can see some particular lines which we attributed to location of 3 nanoplatelets. And here we can see how the Raman spectra looks like. Okay, then about multigraphene. We have used 10 monolayers on multigraphene and deposited it on the same plasmonic structure. We can see how multigraphene is distributed here. We can see some wrinkles or folds here, and here these gold nanodisk are located. Okay, if we zoom this area and try to make TERS experiments, we can see some area which comes from the area where the gold disk are located, and however there are some areas which belongs to Raman scattering from these folds actually. In Raman spectra, these images belong to the mapping by D and 2D modes. So here tierce images in multigraphene are shown with high accuracy, and we can see that in different points of the structure the shift of frequency occurs. The shift is not high, but still measurable. And it gives us possibility to estimate mechanical strain in such folds of multigraphene. And according to literature data, this mechanical stress is about 0.4%. Okay. To conclude, we have realized tierce and nano-IR imaging of single aluminum nitride nanocolumns, and tierce image is dependent on light polarization we observed, and it gives us to investigate different localization of surface optical modes located either in hexagon or two-dimensional aluminum nitride layer. And as to the Schalke-Henide monolayers, we were able to make deep enhanced photoluminescence and deep enhanced Raman scattering images, which allows us to investigate structural inhomogeneities like local defects and mechanical strain in such layers. And also the same experiments are possible to make in multigraphene or even graphene. So, and I hope I convince you that we have realized so-called resonance gap tierce by optical phonons in cadmium selenide nanocrystals and nanoplatelets, especially by tuning gap plasmon energy to the band gap energy in metal nanoclusters and gap plasmon energy to the band gap energy in a semiconductor nanostructure and the laser exciton energy. Oops. Sorry. Oof. Okay. Just I would like to summarize that. Not easy. Huh? Okay. Thank you very much. So. I would like just to say that near-field optical and infrared spectroscopies are considered now as effective tools to probe electronic and optical properties of semiconductor and nanoscale, and I hope much that this spectroscopy becomes a routine tool of optical measurements. Thank you very much for your attention.
Thank you. Open for short questions. Go ahead.
Thank you very much for your presentation. And my question is, as I know, tierce is a very brilliant method for sensing. This is main application. And when we talk about tierce and tierce and Raman enhancing, we want to know what enhancement coefficient of these nanostructures, nanomaterials, and what's the enhancement coefficient of your nanocolumns?
Okay, thank you very much for your question. So, actually, it's not easy to estimate. Sometimes I would say it's not easy to estimate. So we have made a paper which I didn't show here. It was published in 2019. It was devoted to investigation of molybdenum diselenide deposited on such plasmonic structure. We have determined exactly the enhancement factor, and this is about 6 million. Here definitely the enhancement coefficient can be much lower, but the problem is that how to determine actually the enhancement coefficient. For that we should see tierce signal. This is not a problem, but we should know also Raman signal of single nanostructure, and this is not easy. Raman signal is negligible. You see? Therefore, we divide tierce signal on negligible Raman signal and receive infinity. So, and it means it needs some special efforts to determine the enhancement coefficient. So I would say in general it's not simple.
Other questions? I'd just like to ask a short question. It looks for me that all these techniques you discussed are, except IFM surely, are mostly show most of their information they can retrieve in case when you investigate interaction with the atomic or molecular structures. I mean that you investigate how the electronic properties of these transitions are changed when you put your tip close to them. Otherwise, it's very similar to AFM. For example, for imaging, in most cases, AFM gives even better information than to other techniques. So you need to employ interaction, which makes difference. And that is what I did not hear in your talk. Probably it's a different chapter.
You're completely right, but it's make a special sense when you're speaking about chemical interaction. Yeah. But in this case, we are dealing with so-called electromagnetic enhancement mechanism. It means that chemical variation of the nanostructure is negligible. So, and we were able to prove that indeed in semiconductor materials, which we considered here, we had observed electromagnetic enhancement mechanism. So, and we do not introduce any heating effect, any interaction with the surface. But as to plasmonic enhancement by photoluminescence, I would not insist. So you are completely right that we should pay more attention on the electronic scattering when the metallic nanostructure interacts with semiconductors. You are completely right. But first of all, we did not observe actually any significant changes by interaction with gold surface. The only hint that we, or why we use this metal structure enhances photoluminescence signal. And this is, for us, the main advantage of this method.
So basically, this is the employment of Parcel effect.
Okay,
in this case.
Yes.
Okay. Other questions? This is not the case. Thank you, the speaker, again.
Thank you very much.
And we go on further along our program, and the next talk, also actually invited, will be delivered by Dr. Vasilyev, who represents a team of people headed by Lomonosov Moscow State University. And the title of the talk is Atomically Thin Nanosheets of zinc and calcium, chalcogenides, colloidal growth, ligand exchange, and control of exciton properties.
Thank you for short background. So, dear colleagues, first of all, I would like to thank organizers for invited talk. So, in my presentation, I will continue to discuss of semiconductor nanostructures, as Professor Melekhin started. So start with short introduction. I start with colloidal quantum dots. colloidal quantum dots is zero dimensional structures. Their photoluminescence properties easily tuned by change of their size. So they find application, many applications, for example, single photon emitters, light emitting diodes, material for light emitting diodes, lasers, and so in household electronic, for example, Samsung quantum dot TV set. We investigate next generation of colloidal nanostructures, two-dimensional colloidal nanostructures. So we can name it them colloidal quantum wells. These are nanostructures with two-dimensional electronic structure, and so we can modify density of states. We investigate atomically thin nanostructures. Well-known example of atomically thin monolayers is metal dichalcogenides. In this case, it is very simple to prepare one monolayer. We may exfoliate system. So we obtain one monolayer. What is the situation for non-layered materials? For example, zinc or cadmium chalcogenide, well-known semiconductor for optical application. So in this regard, we develop a method for preparation these non-layered semiconductors only half of nanometer thickness. So in this case, semiconductors have a hybrid composition. In addition to inorganic part, we have organic ligand attached to the surface. So we grow these objects by colloidal method. We grow in a colloidal solution. We realize two-dimensional growth in non-polar solvent in a moderately high temperature, and stabilizer was lactic acid. In the case of cadmium chalcogenide, two-dimensional cadmium chalcogenide, we blocked growth of basal phase with use of acetate group, organic acetate group. In the case of two-dimensional zinc chalcogenide, we use somewhat modified method with formation of lamellar structures as solution in which the zinc monolayers grow. And we exchange a ligand. This is additional degree of freedom for modifying of optical properties using interface transfer method. So we use thiolate ligands and carboxylate ligands. Here's a morphology of two-dimensional cadmium chalcogenide nanosheets. We can see faceted sheets with the lateral dimensional up to several hundred nanometers, and rolled up nanostructures for cadmium selenide, also with lateral dimensional about several hundred nanometers. The thickness was about 1 nanometer or lower. This slide demonstrates two-dimensional zinc selenide nanosheets. We we can see also nanosheet with lateral dimension up to 100 of nanometers. These objects were atomically thin crystals, monocrystals. Here, clear faceted sheet with half of P angle and quarter of P angle, and selected area electron diffraction show us pointed diffraction. So this is monocrystal. In the case with use of high resolution TEM microscopy, we show the thickness of this sheet with cross-sectional view. We found only 3 atomic plane. This is about half of nanometer thickness. Optical properties. Optical properties demonstrates exciton series at room temperature. We found fundamental excitons connected to gamma point of brilliant zone, and high energy series of high energy excitons related to points other than gamma. With increase in thickness, we systematically change position of exciton bands in absorption. So we observe step-like batachromic shift with increase of thickness. So we synthesize our structures with precisely of 1 monolayer. So this is 2 monolayer, 3 monolayer, 4 monolayer thick nanostructures. Also we observe exciton luminescence. Exciton luminescence was very narrow, have a narrow band, about 8 nanometers thick at room temperature. For ensemble of nanostructures. So all nanostructures have the same thickness. We can see by our eyes bright luminescence in green for cadmium telluride. Also we observe trap-assisted luminescence, very intensive trap-assisted luminescence, broad luminescence. Here cadmium selenide nanostructure solution, and the luminescence under UF excitation. And we construct white light LED with very high effectivity. Here, white light emitting of these nanostructures. Colloidal zinc selenide nanosheets have also demonstrate exciton absorbance. So we can see narrow exciton bands here and here, series of narrow exciton bands at UV part of spectrum. Ligand exchange. So these nanostructures involve organic molecules attached to the surface, and if we change organic ligand, we change the property of our nanostructures. Here we find that flat cadmium telluride nanosheet spontaneously rolled up in multi-wallet rolled up nanostructures. So this is the effect, we name it by spontaneous folding, and we write a paper in the chemistry of materials. So it's very interesting structures. it's rolled up nanostructures with precisely defined interlayer separation. These nanostructures are very homogeneous. So all our nanosheets spontaneously folded in rolled up nanostructures. Effect on effect on optical properties when we change carboxylate ligand to oleic acid on thiolate ligand, some thiols, we find batachromic shift of all exciton series. All band shift to red range. For cadmium telluride, for cadmium selenide, so two reasons affect on this effect. Increase in effective thickness due to strong hybridization of sulfur from thiol group to the cadmium basal planes. And we add to sulfide plane. And mechanical stress effect. Here shown, the slides show size-dependent properties. So we add two sulfur plane on cationic basal plane. So the thickness is, we add one monolayers to the thickness, and we shift excitonic bands to thicker nanostructures. Here, dependence of energy of transition for inverse root of thickness, and we clear can see size-dependent effect. So sulfur hybridizates to atomic plane. So we use next type of ligand, carboxylate ligand, with different lengths of carbon change. We use carboxylic acids. We change oleic acids to acetic acid, and then for carboxylic acid with different chain lengths. So we change interlayer distance, so we clear see the change in carbon chain length. We analyze this nanostructure by small angle X-ray diffraction and find that they compressed when we introduce small chain or carbon chain for short carboxylic acid. And then we analyze Fourier transformed infrared spectroscopy. And we find that carbon-hydrogen vibration strongly shift from their position for oleic acid. We find strong change in wave number of carbon-hydrogen vibration. From literature is related to high pressure in this high pressure on carbon on alkane molecules. So the carbon-hydrogen distance reduced. And we estimate the pressure in ligand layer about 3 gigapascal. So is steric hindrance between molecules resulted in high pressure in ligand self-assembled monolayer. We clearly see that these are self-assembled monolayer for methylene vibration. So this high pressure result on optical properties. Ligand layer deformate semiconductor layer. So compressive or tensile deformational at semiconductor ligand interface caused by mismatch between available space on basal cation terminated plane and size of seat of ligand resulted deformation of semiconductors. So we can clear change of exciton luminescence position. So it's a new way to fine-tuning of exciton energies. So this is my co-authors from Moscow State University. So this is two-dimensional cat. This cat is not so thin as our nanostructures, but somewhat is a nice cat. Thank you for your attention.
Thank you for keeping your time. The paper is open for questions.
Thanks, very nice talk. I wonder how can you keep these structures uniform in terms of the luminescence line? It is not only thickness, it is also the shape, the folding, and anything else. Because with quantum dots, people, colloidal quantum dots, people are now pretty good in keeping orange with orange and red with red and so on. And how do you do it?
These are nanostructures, rolled up nanostructures. So we can see that all of them rolled up. And we can see that for lateral dimensions, we can sum dispersion. Some of nanostructures somewhat longer than other. In lateral sizes, we have a dispersion like classical nanoparticles. Dispersion of size about 10%, 20%. In the thickness, we see that all of them precisely have only three planes. Here, 3 planes. And all of them have the same excitonic energies. I'm sorry. All of them have same excitonic energies. So we have the same bandwidth as for ensemble as for single nanocrystal. So all of these nanostructures the same thickness, precisely with precising of one atom. Why? I don't know. Is a method of thickness. So what is this? This is chemistry of mystery. I don't know.
You are a chemist, we are sure, not mystic. But in some slides I've seen 3.5 monolayers. So
3.5
it is
about
3 and.
If you see here, anionic, cationic, anionic and cationic. Cadmium terminate the symmetric nanoplate with cationic termination. So cadmium one monolayer, additional one monolayer. So we terminate uncompensated electrical charge by charged ligands. So we must use ligand. This is hybrid system.
Thank you, Roman, for presentation. And probably a general question. You are using organic material to change optical properties of semiconductor materials.
Yes.
What's the general idea of to merge organic and non-organic structures?
I see. General idea involves the simple fact that we hybridize organic molecules to compensate the charge of semiconductor layer. So in any case, we involve organic molecule. So we think why we cannot change these molecules. So it's very this very interesting results. We can change a type of ligand, a type of acid group of ligand, sulfur carboxylic group. So we change of hybridization of energetic level of nanostructures and organic molecules. Other idea, new type of deformation. Deformation between ligand layer and semiconductor layer. Usually classical deformation at the interface semiconductor, two different size of crystal perimeter and deformation. So it's new type of deformation between organic and inorganic.
So my question is similar to that given previously. So you told that you have just only one thickness of nanoplatelets. But I remember your paper in Journal of Luminescence where you have shown that something like 5% of the platelets have the thickness of 3 monolayers, all others have the thickness of 4 monolayers, or vice versa. So how it's related actually with
Yes, I see. I show you these results. Here, luminescence, exciton luminescence, we find main peak 3 monolayer cadmium telluride and 2 additional narrow peak related to other population. Our nanosheets grow as population with strongly same thickness, but if we change the condition, one populations can, in addition to one population, can grow other population. So in parallel growth. The nanostructures with this absolutely homogeneous. It's impurity of additional populations.
Okay, thank you. Chemistry is always a little bit of magic. We go further. And next talk, regular talk in our program will be delivered by Dr. Arjanov. The title of the talk is Electron-Phonon Coupling in the ensemble of colloidal quantum dots, combined study by spectral and time-resolved methods. This collaboration of Moscow Pedagogical State University, Lebedev Physical Institute, and the Institute of Spectroscopy of the Russian Academy of Sciences.
Thank you very much for present the name of my presentation. And today I will talk about electron-funnel coupling in ensemble of quantum dots. And the main motivation is how we determine spectral properties of colloidal quantum dots and nanocomposites based on them, and what's experimental method we may use to determine internal dynamic in quantum dots. What's the quantum dots? As we know, is a very small piece of semiconductor, and the size around 10 nanometers, from 3 to 10 nanometers, and we can use different semiconductors to synthesize these nanoparticles. And the main properties, spectral properties of these nanoparticles is wide absorption spectra. We can excite quantum dots using LED or UV. And when we second property is quantum size effect, and we may choose the size of quantum dots, and we can tune wavelength. And we can use these quantum dots in different applications, like LED displays, like Samsung, and different new materials like conversion, quantum technologies, and other. To determine internal parameters of quantum dots, we can characterize them. I start to talk about only colloidal quantum dots because it's very cheap and low cost synthesis of them. And to prepare a sample, we used two different methods. It's usually spin coating methods when we rounded glass substrate and drop a sample with quantum dots. And the second is blade coating methods, when we spread solvent with quantum dots on a glass substrate, and we have very homogeneous sample. And you show, as we see, we have spectral luminescence and absorption spectra for these samples, and TEM images and size distribution for these quantum dots. And to determine internal parameters, we want to know what the theoretical model we use. As Annie knows, there is a good model was created by Varshny, but its model works with only bulk semiconductors. When we measuring temperature dependence, we can determine energy gap in semiconductor, but there is very low parameters, empirical parameters we get, and we can describe what process inside quantum dots. And the second model, it's model of O'Donnell and Chen, and they show that talk about energy gap, temperature dependence of energy gap, and we can get from this model two parameters like Hwang-Rees factor that show us force of electron-phonon coupling, and we can get second parameters is average phonon energy. This is very important because it's open us the method to measuring phonon energy without using Raman technique, and we work with this. And I talk about many experimental setups that we use. This is temperature dependence measurement when we have excitation laser, helium cryostat, and spectrometer to detect that exciton luminescence. And when we changing temperature, we can register it and analyze spectrums. And the second setup is incoherent photon echo. In this setup, we can measure ultrafast dynamic in our sample, just vary time delay between pump pulse and probe pulse. So I talk about temperature dependence of luminescence spectra. We measure it, this dependence on different samples. This is quantum dots glass substrate, quantum dots in polyisobutylene, and other. So we have temperature dependence with pure quantum dots on glass and quantum dots in amorphous matrices. So we can determine peak position of the spectra and calculate it to exciton energy and get dependence, temperature dependence of energy band gap. And when we use using O'Donnell-Chen equation, we can get a data set of parameters for our systems, like energy of band gap, Hwang-Rees factor, and the energy of average energy, phonon energy. So the next step, I will talk about directly measurement of local phonon energy using triple monochromator. So we have a spectra of Raman scattering, and we have a peak around 206 centimeters, and we can calculate it to energy. It's around 25 milli-electron volts, and this this is near value for calculated energy from O'Donnell-Chen equation. And the third method we used, it's photon echo. We can get different decays for photon signal echo, and we can get value of bandwidth to determine what properties play in bandwidth increasing or decreasing when we change the temperature. And we have different dependencies for quantum dots in different matrices, and we can recalculate the temperature dependence for photon echo, and we have around 2 milli-electron volts with at the low temperature, and for a bulk material we have around 40 and 80 milli-electron volts. This picture I show temperature dependence for photon echo experiments and for single quantum dot spectroscopy, and show we have a different hierarchy of process what we have when we decrease temperature. At room temperature we have just bandwidth of semiconductor quantum dots, and when we decrease temperature we have a narrow spectra of quantum dots. It seems to be talk about different processes like spectral diffusion and switching like on-off blinking quantum dots blinking, and the second result is I get a data set of temperature dependencies for different quantum dots, and we can calculate it band gap energy and the energy of local oscillator and factor for increase, and we get of course 2.1 electron volts that characterized band gap energy for bulk semiconductor, and the second important parameter is average local phonon energy is around 20-25 millectron volts that we get in temperature dependence of luminescence, and we get it in Raman spectroscopy that show us to we can use these methods to determine these parameters, and parameters is equal with different articles. Okay, and this is the main results, and I think you have any questions for me. Thank you for your attention.
Are there any questions?
Should I have a couple of questions? First of all, how did you calculate, how did you derive Huang-Fi's factor? Did you do this from Raman experiments?
Okay. To calculate Huang-Fi's factor, I use only results from temperature dependencies.
But as far as I know, this is determined like a ratio between intensity of the first and second.
No. Huang-Fi's factor we can calculate using only energy of band gap, not only intensity.
Okay, then the slide number 11 maybe.
Mm-hmm.
So this is a long table, and I'm wondering on the second column actually. You shown here that the average energy is 20-25 millectron volt, but if you look at the very last value, this is 11. How it can be? This is huge difference.
Yes, this is we have a big difference because we have different structures of these quantum dots. I show at this table
this is absolutely not possible.
There is no only colloidal quantum dots. We have a monolayered quantum dots. We have bulk semiconductors.
But you're speaking about the same phonon, cadmium selenide phonon, right?
Mm.
The change of the frequency twice, it's impossible. So no chance.
This results from different reports.
No chance. Please believe me. So if you
change the temperature from the room temperature to the helium temperature, the change is only 4 reciprocal centimeter. This is just only 2%. If you change the mechanical stress, you can use a huge mechanical stress. Then you can change by 10%. Here they change twice, so it's impossible. So it means that either this is wrong results or these values belong to other phonons.
Okay, thank you.
Okay. So there are no more questions. Thank you again also. Mostly move to the next talk, which will be given by Dr. Tarasevich. The title of the talk is Testing Different Models of Fluorescence Blinking in Submicron Perovskite Crystals by Studying Photon Statistics. Тут ошибка в названии. Okay.
Dear colleagues, hello everyone. My name is Alexander Tarasevich, and today I'm going to tell you how to test different models of fluorescence blinking in semiconductor perovskite submicron crystals by studying photon statistics. The outline of my talk is on the slide, and let's start from the methylammonium lead triodide perovskites. To begin with, I'll say that MAPI is a perovskite crystal and has the next crystal structure, and in the bottom picture you can see the images of MAPI films from scanning electron microscope and also luminescence map. And as you can see, there is some domain structure, and each domain has different quantum field, and moreover, this quantum field is changing in time, which called blinking. But these films are very interesting and promising material for optoelectronics, and also it is easy to cheap, easy and cheap production to product. Okay, but to study the blinking behavior of luminescence, it could be more convenient to study some submicron crystals of this perovskite, and in this graph you can see the fluorescence intensity trace, and there are some intensity levels corresponding to some values of quantum field. To determine this behavior, there are two different models. First is called emitting site model, and it suggests that there are some emitting sites based on some defect in the crystal, and this emitting site can be in two states, when it is active. There are two parts in our luminescence. It's luminescence from bulk part of sample and from the emitting side. And when it's quenched, there are only bulk part of luminescence. And the next model is super trap model. Super trap model suggests existing of so-called super trap. It's some metastable, very active channel of non-radiative recombination, and when it is active, the rate of our recombination, non-radiative recombination, highly increased, and the quantum yield drops down. Okay, but let's take a closer look to the emitting site model. Each emitting site is effective quantum dot, and as we know, quantum dot luminescence of quantum dot changing due to the Auger processes that is very effective in small volume, and also the Auger processes leads to the anti-bunching effects. So quantum dot is a single photon emitter and can't emit two photons simultaneously. If you used to see these effects of anti-bunching can be observed in second-order cross-correlation function, like falling of the function across small delays. And if you used to see this function like some continuous form, I like to say that there is the same thing, but just in our case, when the distance between distance between excitation pulses is much longer than the decay time. This function will looks like some peak function, but if we will increase our pulse rate, these peaks will be intersect, and finally we can transform this function to the more familiar form. Okay, as I said, according to this model, in our crystal there are two part of emission with different statistics. First is bulk emission with Poisson statistics, and G2 around 0 is equal to 1. And the next part is emitting is sub-Poisson statistics with G2 is equal to 0. And this mixture should give us some averaging picture, and the value of G2 should be from 1 to 0 if this model is relevant. And we can check it in our experiment, and this is our experimental step. It is a home-built luminescence microscope with 3 detection scheme. First is EMCCD camera to detect luminescent images. The second is spectrometer to spectral measurement. And the second is Hanbury-Brown and Twiss scheme to photon statistics investigation. Although this scheme can be operate in wide field mode as well as in confocal mode. Okay, we conducted our experiments, found out that the blinking dynamics depends on excitation power, but also there is no any partial anti-bunching in each experiment, and one can object that the contribution of the photons from single photon emitter is too small to detect it in our experiment, but we can increase this contribution. Let's calculate correlation function not for all photons detected in experiments, but only for photons corresponding to some level of quantum field. And according to this model, for photons for lower intensity level, there should be Poisson statistics because in this level there is only bulk emission, and as a result we increase the contribution of photons from single photon emitter for upper intensity level, and we did it, and in the right part of the slide you can see the expected values for emission site model of G2, and as you see we again gave the one, and that said that there is only bulk emission, and more interesting is this slide is more interesting because in this case the power of a single photon emitter should be much more than the power of bulk emission, and in this graph you can see the expectation value for emitting site model depends on the rate between powers of single emitter and bulk emitter, and in this case the value of G2 should be 0.2, and as we see in this slide, this function, it's again the one. And what about super trap model? Super trap model. In a super trap model, there is shouldn't be any anti-bunching effect because there is no mechanism that prohibited maybe to emission of two photons simultaneously. It just make faster our non-radiative recombination and drops our quantum field. Okay, to conclude, I'd like to say that the absence of anti-bunching supports supertrap model. The approach to check the emitting site model was proposed, and the result was presented in this article. Thank you for your attention. If you have any question, I'll be glad to answer them.
Thank you. Are there any questions? Comments? I have a very short one. So your statement is that the only one model, as you see it, is a trap model.
Yeah. Not only one, but the main point.
I cannot see a variety of models you presented. There are other models. Which one?
No. The main model now, it is a supertrap model.
Okay. So that yeah. Okay. Other questions? Okay. At this point, we close this talk. Thank you very much again to the authors. Finally, Svetlana.
Yes, I'm here.
This is Viktor Zatkov. Hello from Moscow.
Can you hear me?
Yeah, perfectly.
Yes, very
So,
good.
I'm pleased to announce an invited talk by Sveta Lukasheva from Rochester. Thanks to nowadays situation in the world politics, we cannot name the organization. No, this is a requirement. Anyway, Rochester, an independent researcher.
Can you see my slides?
Yeah, we see them. The title of the talk is Photomodification of silver nanocubes by patch plasmonic nanoantennas by visible laser light. Svetlana, go ahead.
Yes, okay. First of all, best wishes from Rochester, New York. And thank you, Viktor Nikolaevich, for introduction and inviting me to this great conference. So I will speak about photomodification of silver nanocubes for patch plasmonic nanoantennas by visible laser light. This photomodification of my talk is different from changing the shape of metal plasmonic nanoparticles by laser irradiation by melting. This is considered in papers of Baltasheva, Shalaev, and Oliver Benson group. I will speak about photochemistry. Here is outline of my talk. In few words, I will describe patch plasmonic nanoantennas. Next will be experimental setup and results, spontaneous photoluminescence spikes, and stepwise photoluminescence increase from silver nanocubes, which should not fluoresce. And next will be atomic force microscopy of cubes after irradiation, spectral measurements, and possible mechanism of these parasitic photoluminescence effects that can influence emission of emitters within nanoantennas. Application of this research room temperature single photon sources. I would like to say that from all known photonic nanostructures, plasmonic nanoantennas provide both the highest reported emission rate enhancement and highest photon flux increase from single emitters. Not only single emitter, but particular to this subject, single emitters. And from all types of plasmonic nanoantennas, the highest Parcel factor with increasing emitters radiative decay rate with maximum 1,000 times, and total fluorescent intensity maximum reported 2,300-fold enhancement were obtained with metal plasmonic patch or gap nanoantennas. And remarkable results were obtained with these nano-antennas, up to 35 million photon counts per second from NV center nano diamonds, coupled to silver patch nano-antennas reported in Shalaev-Baltasheva groups. Most of reported patch nano-antennas consist of emitters situated in the dielectric gap, nanogap, small nanogap, between metal nanoparticles of different shape, cube, triangle, and so on, and a metal film, metal mirror. For visible spectral range, usually silver nanoparticles are used as part of this patch nanoantenna. And here you can see numerical modeling of parcel factor for silver nano antenna, patch nano antenna for NV center up to 1,000 times. So this is right now an antenna with highest parcel factor. Silver plasmonic colloidal nanoparticles are used not only nanocubes, but nanocubes are very convenient, in many papers reported, used in patch gap nanoantennas for visible light. So for visible light, mostly silver. Gold does not work. And you can see different options with this. I put the pictures of nanocubes. This is from Shalaev groups, and even with nanocubes, plasmonic enhancement of brightness in organic light emitting nano antennas. And this cube can be put part of more complicated nano antenna and use it in microcavity for enhancement, combination microcavity, and this simple, relatively simple nano antenna. And another step with this cube, very convenient to make metasurface from cubes, here a metasurface from gold nanocubes, and coupling, possible to obtain coupling, and was reported coupling, but this is gold, but with silver for visible, with photonic structure, with lattice plasmonic gap modes with narrow resonance, and with plasmonic modes of gap mode of an antenna with cube. This is interesting direction. So it's worth to study. And our goal, room temperature single photon source application, enhancement of fluorescence of single emitter nanocrystals, nanodiamond, and mostly a rare earth doped nanocrystal to enhance weak fluorescence from single ion of rare earth. And we started to work with nanodiamond and with patch nano antenna, with metal mirror and silver nanocubes. And we observed very strange behavior. And I will report about strange behavior on separately. After this observation, we started to begin to study these silver nanocubes, what is going on. Our sample, 100 nanometer silver nanocubes from nanocomposites. This is in main research. It's easy to buy from this company, these silver nanocubes, and from environment, with silver nanocubes protected by 3 nanometer layer of polyvinyl pyrrolidone, PVP. It's very common. We used silver nanocubes, either spin coated with different concentration from solution and or drop of on cover glass slip. This is how they look. This is electron microscopy, and this is maximum absorption. Here is our experimental setup, single photon generation characterization units. This is home-built confocal fluorescence microscope for single emitter fluorescent microscopy and spectroscopy with electron multiply CCD camera and Hanbury Brown and Twist interferometer and several lasers. In this research, we use a 532 nanometer and 633 nanometer laser excitation continuous wave. High numerical aperture oil immersion objective, and power was, intensity was less than 100 kilowatt per square centimeter. Here is user interface of our setup. We have two detectors, and this is confocal microscope raster scan images of each detector, and we can focus, stop on in any area and observe, collect data either for anti-bunching or here is time traces. And because two detectors, two different color of time trace. And usually we are using 5 milliseconds per pixel. Each pixel, this is pixel, 5 milliseconds per pixel. And count in counts per pixel. And here are our results. So first of all, we observe some features with single emitter behavior, but this 100 nanometer silver should not fluoresce. And we observe, you can see semicircle like a single molecule and stripes, and we have many such images. And we stopped and we started to record time traces from this area. And we observe after several minutes accidentally appearance of high intensity spike. And interesting that this spike even brighter than single emitter fluorescence, up to million, even we had 1,200,000 counts per second. So, and this is raw data, and this is already data processing of these spikes, and duration of spikes varies from 0.1 second up to few seconds. And they appeared, and we had many samples. I had students with almost similar results, with fresh sample and the sample after 1 year. And you can see data, this time traces, units 100,000, units 100 seconds. And you can see spikes, and also in addition to these spikes, high intensity spikes, we observe stepwise photoluminescence increase. So if this is 250, you can see here 107 times increased photoluminescence. And this is raw data and processed data. And these spikes, 900 kilocounts per second. So possible mechanism. So we think there are two possible mechanisms, but high probability that we have for the induced creation of small silver nanocluster. It is well known that small silver nanoclusters, fractals on the silver on noble metal surface, fluoresce, has high intensity fluorescence. And there is the whole direction of research with interesting application of Georgia Tech of very bright metal nanoclusters but behave as single emitter with observation even photon anti-bunching for some of these nanoclusters. We did not observe anti-bunching. We tried, but from this nanocluster we did not observe. Also, possible SERS instability, surface enhanced Raman scattering instability. And I will show later slides with surface enhanced Raman scattering of PVP of this polymer, 3 nanometer polymer, and we observe instability, but we don't think that this is the reason of this high intensity photoluminescence. And here what I can show from Georgia Tech, Robert Dixon, so also we observe appearance of bright after some irradiation, but they investigated silver oxide film, and on this film they observed this high intensity, bright, multicolor fluorescence, and with also single molecule behavior, and this is where results they even observed anti-bunching. Here is our micrograph of atomic force microscopy after irradiation of these nanocubes. We have some features, some clusters, but this cluster 30 nanometer, we did not record smaller cluster, usually clusters of up to 10 nanometers, very bright. So, and the same clusters, similar cluster, under the little bit different condition, but also photochemistry, observed in General Physics Institute after irradiation by visible laser light of silver iodide. So here is a raw spectra of this sample. And not always we see with surface enhanced Raman scattering, all this line exactly a line of PVP. So this is 633 nanometer excitation, this is 532 nanometer excitation. And we had the video with instability, but problem with this very low intensity. And even with electron multiplying CCD camera, we had 10-second exposure time, although with 1 second we also observed. And regarding source instability, it's present, and here is the beta video what we have, and I will show you this source instability. This is gold from this paper. This is gold colloidal particle, and also covered by PVP. And you can see the source instability, it exists. But we did not observe, and the same, but these authors did not observe the high intensity spike, so it may not, can contribute this mechanism but not so significant, maybe. And in summary, two effects were observed that may influence performance of single photon sources with patch plasmonic nanoantenna based on colloidal silver nanoparticles. And I will repeat what we made experiment on under continuous wave laser excitation. And in some papers reported observation of anti-bunching with silver nanoparticles, nanocubes, under pulse radiation, but continuous wave fail. Maybe this is the reason. We observed spontaneous photoluminescence spikes up to 400 to 900 kilocounts per second, and even higher than million kilocounts per second. Usually colloidal nanocrystal quantum dots and nanodiamond 200 kilocounts. Bright quantum dots can be up to 1 million, but this is the same level of intensity. So from silver nanoparticles coated with few nanometer of PVP, but I think that this is silver effect, the small cluster. And we observed under 532 nanometer and 633 nanometer red light irradiation. And under the same condition, we observed that this stepwise spontaneous photoluminescence increased up to several times. And this photoluminescence effect should be taken into account when we are working with silver plasmonic nanostructures. So these silver structures induce photoluminescence from silver may influence purity of single photon emission with silver nanoantenna least at continuous wave laser irradiation. And silver is not good material on an antenna. It looks in numerical modeling, looks very good for visible light, partial effect enhancement, but what this effect parasite can ruin real device. And these are you can find details in this publication. And these my students who contributed, these are my students who contributed to this work. And thank you for listening. And questions, please.
Thank you, Sveta. The paper is now open for questions. Andrei?
Thank you very much, Svetlana, for the very nice presentation. It's Andrei Naumov. So I just wonder about this effect of SERS blinking, which you shown. And my question is, what do you think? Maybe it's just some small diffusion of your material around some hotspot, or what is the microscopic nature of this blinking?
The microscopic, this is a good question, and this is also our question. This is not you are speaking about what blinking, but we observe blinking when in raster scan, you can see what this is blinking semicircle, but on when we focus on the specific area. So initially we observe low fluorescence and intensity spike, accidental spike. This is not blinking.
Okay.
This is some process, and we think that this is maybe photochemistry, creation of bright clusters, because with noble metal fluorescence there are a lot of paper. And mechanism, to tell the truth, there are many mechanisms depending on size and so on. Our suggestion, this is photochemistry on the surface.
Okay, thank you. Thank you.
Mm-hmm.
Alexander Melekhin from Novosibirsk, Zaskin. Actually, I have two questions. So I was learned from chemistry that if we will take a table, silver spoon, it will be darkened with time. Yeah? And this is not due to oxidation of silver, but due to sulfidation. The question is why you consider that your silver nanocube undergoes oxidation but not sulfidation.
It was a very low sound. Can you repeat?
Okay. Probably I will speak maybe shorter. So normally chemist says that it is very difficult to oxidize silver. First of all, silver undergoes sulfidation. Why you do not consider sulfidation? If you have sulfidation,
it's a very good question. So we consider oxidation, and we think that maybe a combination of oxidation, and within this oxidation, we have this cluster, small cluster. Why from the 100 nanometer silver, we have this small silver cluster. So it can involve oxidation because it's after some time.
So I'm not speaking about oxidation.
Did you?
Do you hear me? I do not speak about oxidation. As I was learned from chemistry, so oxidation is almost not possible. So the most simple process is sulfidation, covering by sulfur atoms.
I don't know where did you learn from chemistry that oxidation of silver is not possible. So it's possible, oxidation of silver.
It is possible, but with high temperature. Then
I would like to check that because my knowledge is that possible not only high temperature and especially under photo under irradiation.
okay. Then the second question. So I'm
Silver
dealing.
is not stable material, to environment.
I'm dealing with tip-enhanced Raman scattering, and in our experiments we have used silver cantilevers with the size about 100 nanometers. During tip-enhanced
So
Raman...
this is very interesting. Who is asking question?
My name is Alexander Melekhin from Novosibirsk.
Oh,
This is Centrum of Russia.
Just a moment. I should write your name and we should contact. And thank you for your question. Alexander
Melekhin. I was second author of this session. So the question
very good.
is the second actual question. So when we perform tip-enhanced Raman scattering, we always see the spikes. So in TERS community, this is common, and people say this is just due to flying carbon species in air, just simply dust. What do you think about that?
Excellent point. I know this paper Lakovitz. I did it, he wrote that possible on fractal, but intensity spike, you didn't observe such high intensity. The problem with a very high intensity spike up to 1 million kilocount. In conventional CERS, what this is paper famous Lakovitz, for instance, if you know these papers. So this on fractal, on noble metal film, yes, observe what with spikes, but not such intensity, and no observation of stepwise photoluminescence. So thank you for your question, and I will contact you. Maybe we will find more deep to understand the mechanism. But the problem with this is very high intensity spike, not like in CERS, conventional CERS. I check all papers on CERS. In Columbia University also work in the same direction.
Svetlana,
but not,
I have a short question. Do you observe similar enhancement in photon counting while applying pulsed radiation, not CV?
The pulse enhancements a lot of papers. But Shalayev group, who is asking question, I can send you references. And in my talk, there are references.
So in numbers are the same? Okay. Thank you. At this point...
Thank you for question. And I will contact Alexei, I forgot your name, Milentiev. Okay, I will contact. Better good, but in equations, maybe we will find the real mechanism.
Okay.
But this is not simple.
Svetlana, the organizers will send you the contacts via email.
Pardon me?
The organizers will send you the email contacts via email. Okay.
Okay, thank you.
Thank you very much. Bye-bye.
Thank you for question.
Yeah. At this point, we close the session and go to some coffee if you have time.
So, dear colleagues, let me start the last session this day. The first speaker, Daler Dadajanov from St. Petersburg. Please give your talk.
Good day, everyone. Thank you for invitation. It's actually a great opportunity to be here as a young researcher. My name is Daler Dadajanov. My topic is devoted to novel physical method for 2D chiral metasurface formation. My talk is devoted to the several sections. I will tell about some short description about chiral plasmonics, how can we make chiral structure using a spectral hole burning technique, and two sections with results that devoted to formation of chiral silver metasurface on dielectric substrate, and another one inducing optical chirality from achiral gold nanosphere embedded in nanoporous silicate matrices. Conclusion and acknowledgement. Actually about chirality, describe geometrical property of molecular structure which cannot be superimposed with a mirror image. The easy example is our hand. We have a right hand and a left hand. In the same situation, we can be with molecules that can consist in the same atoms, but have a different composition. It's called L enantiomer or D enantiomer. In terms of chiral plasmonics, it has attracted increasing the interest due to the modern nanofabrication technologies and wet chemistry technology, because it's possible to fabricate very complex and well controllable chiral nanoparticles. The applications such as using this chiral metasurface is applying for the photodetectors with detection of specific light with circular polarization, for example, optical modulators, and also biosensing. If we're talking about the plasmonic nanoparticles, we know that it's very sensitive to the dielectric environment, and changing the dielectric environment leads to the shifting of plasmonic frequency. In this case, it's also possible because we can focus on not only the shifting of plasmon frequency, but rather also on a circle diacheism spectra. But we have some limitation. It's very challenging to fabricate such a structure. It's the procedure is complex, and if we're talking about metasurface, the production of such a metasurface is very expensive. In our case, we propose a novel and a large-scale method for formation of 2D chiral metasurface using a spectral hole burning approach. A couple of words about this method. This method actually was well studied in our laboratory in ITMO, particularly my colleague, Professor Vartanyan. They consider the spectral burning hole method on the granulated silver nanofilms placed on the dielectric. For example, it has it has very broadened spectra that the reason of such a behavior is inhomogeneous distribution of plasmonic nanoparticles on the surface. And if we apply the laser irradiation or such a structure, we can selectively, firstly, heat nanoparticle and change the shape of nanoparticle. And what happens in the spectrum, we can see some spectral gap or hole on the spectra. This technique was applied just only to study the phasing time and some anisotropy properties. And we move further, apply it to achieve chiral nanoparticles. Firstly, this part is considered two type of sample, nanoparticles deposited one, and another one is annealed one. And in this case, we see some island-shaped nanostructure. It was silver, and here is some rounded nanoparticles. Here is some parameter what we use. The thickness, equivalent thickness for these two cases, it was the same. It's around 12 nanometers. What happened next? We irradiate the sample with circular polarized light at the second harmonic of neodymium laser. It's 532 nanometers. It's both case for right-handed polarization and the left-handed. What we see, firstly, we investigate the optical density spectra. The dashed line is for the right-hand circular and solid line for left-handed. In left spectra is shows the absorption of not annealed silver nanofilms. We can see as energy, laser energy increased here. We see some reducing optical density and some spectral gap in the region of wavelengths of incident light. Unlike this situation, we see another case, a behavior for more rounded nanoparticles. It's more favorable for us because this plasmon resonance frequency is in the same region of incident light. And also see decreasing optical density in emerging of spectral gap. To verify if we have a chiral structure or chiral ensemble on with our sample, we measure the circle diacheism spectra. Circle diacheism measure the difference of transmission for left circle polarization light minus right circle polarization light. And what we got in this case for not annealed sample, we got very strong circular diacheism around 120 millidegrees with very broad spectra. And we also verify if we apply opposite circle polarization, what we got. And we got opposite signal. And calculate J factor for the maximum results, amplitude of circle diacheism. Actually, it's equal up to 0.5. And this value is comparable to the value what people got by using E-beam lithography or focusing ion beam method for fabrication of periodic metasurface, chiral periodic. Another case we also got for structure what was annealed and we see, in this case, B-signate behavior of circular diacharism. In this case, yes, G factor is a factor of dissymmetry of chiral structure. It's a bit lower, and after that I show what is the structure actually got the same B-signate spectra. And here we try to explain what happens if we anneal such a structure, and how to verify how chirality arises in our system. Actually, before laser treatment, we assume we have a equally amount, let's call it racemic ensemble of left-handed nanoparticles and right-handed. And now after the radiation, we eliminate one of the part, make some disbalance. And what we got after the annealing, annealing should lead to the more spherical nanoparticles. And what we got, if a spherical nanoparticle will be around for the whole ensemble, the circle diacharism will be zero, approximately zero, without any substantial peak as showed before. Here is the ECM images. After irradiation, we studied dependence on the laser energy fluence, because there are two effects. Firstly, radiation melt or shape nanoparticles, and another effect, it's not good for us, it's ablation process. And we found the optimized value of laser energy at which nanoparticles are not ablated. It's around 21 millijoules per square. Another, here is, from this case, we choose some region of interest that give us the B-signate structure, and apply it numerical calculation for calculate the circle diacharism. If we found that such as ensemble of three nanosphere on the dielectric substrate with a different radius, give us B-signate, this signal of circle diacharism. Yes, if we compare with the previous one, it's a little bit broadened, but we can in further optimize the system, but we found that such a structure give us the same behavior. Another one, it's also very unique and interesting result here. It's transformation of achiral colloidal nanosphere that was embedded to nanoporous silicon matrix, shortly called NPSM, to the chiral one. Here is firstly sensitized by conventional method of seed-mediated growth procedure, colloidal nanoparticles with a size around 20 nanometers, not 50 nanometers average size. After that, we deposited by drop casting on the silicate matrix, proceed with some annealing procedure, because here is some organic contamination from the C-tap, and sample was not transparent. And after that, also applied the laser irradiation, as mentioned before. What we got here, actually, we measure the spectra of colloidal nanoparticles, and it have the same position of nanoparticles inside of silicate matrices. Also measure this circle diacharism without any laser treatment, and we see there is no any significant peaks. In this case, we assume that silicon matrices compose from the 2D like structure, like L shape and gamma shape. And also, probably, if we place it in volume, there can be the composites that form 3D structure, like a helix one. After that, we irradiate with a circular polarized light, with right circular polarized light E. It leads to the melting of nanoparticles that resonantly absorb incident light. It should be mentioned that we firstly irradiate the front side where the nanoparticles was deposited. And what we got before, after that? After that, we measure the circular dichroism from the front side. We observe the very strong circular dichroism band around the wavelength incident light. Non-obvious case was observed if we rotate the sample to the respect of probe beam. If we see there is any band as we see in front side. We call it Janus effect to the very famous sculpture. It has different faces if we rotate the sculpture. We assume that after the radiation, we melt nanoparticles that was resonantly absorbed, for example, right circle polarization light. In this case, remain only L shape and helix that also absorb light with a left circle polarization. But if we rotate the sample, now L-shaped nanoparticle will absorb opposite case, right circular polarization, but helix will save polarization. In this case, we probably see the reducing of effect of circular dichroism. After that, we decided to check if there any effect from the radiation with opposite on the same structure. Because if we previous cases with the nanoparticle on the surface consider nanoparticles on the surface, there is kind of process of ablation. But in this case, it's possible that nanoparticles cannot be extracted from the porous matrices. It's very attractive for optical modulators. And we just try to irradiate the same structure with the opposite, with a counterclockwise circular polarization. You see the reversible effect where when here we see the also not substantial circular dichroism band, and here we see like a 0-1. It looks like in one side is transparent for the circular and an opposite case not transparent. Okay, its conclusion. In our work we demonstrated possibility of obtaining an isotropic and chiral matter surface using the using optical methods, spectral hole burning techniques. For complex structure, laser radiation led to selectively changes of resonance nanoparticles. First of all, it changed observed when both wavelengths, plasma resonance, and orientation of nanoparticle inside with the polarization, I mean circular left or right, and it leads to the very strong G factor and also a signal of CD spectra. Another results for the structure with rounded shape. Laser radiation leads to a appearance bisignate signal, and we assume this is due to formation of structure closely spaced nanoparticles, like three-shaped nanoparticles with different diameters. And a last conclusion and result is spectral burning techniques was applied to induce chirality, strong chirality in achiral gold nanoparticles in porous matrices. I thank you for my colleagues in ITMO University, also grateful for the Russian Science Foundation for the supporting the research, and a special thanks my colleagues who provide the laser technique. Thank you for your attention.
Thank you for your talk. Please questions to the speaker. Okay. You mentioned about ablation processes which decreased your possibility to produce these substances. Did you play with the pulse duration of your laser?
Actually, we played here is only picosecond pulse duration, but we have results not already published. With a nanosecond, we got more G factor than with a picosecond. Probably duration of pulse duration gives more time for nanoparticles to reshape the structure.
Okay, thank you. Let's go to the second talk. Alexander Sorokov from Moscow State University. Please go ahead.
So, great. Good afternoon, dear colleagues. I'm very excited to be here. First of all, I want to thank organizers for providing me an opportunity to make an invited talk at this conference. Today, I would like to tell you about our research on the optically tunable nanophotonic structures, which possesses the Me-type resonances. And I will start with a brief outline of my today's talk. First of all, I will give you a really brief overview of Me-resonant nanophotonics. I will try to show you why this topic attracted so much interest from different research groups over the globe during the last years. Then I will show you how the structures can be tuned. We will consider different mechanisms which can be applied to provide some active response. Then I will focus on typically ultra-fast optical tuning by photo-induced modulation, which can be provided by femtosecond lasers. After that, my talk will consist of three different projects, different but related. The first one will show you our results for tunable diffraction with gallium arsenide metasurfaces. In the second, I will show you how this approach, which we will consider in the first topic, can be applied for tunable coupling of light onto the optical chip, also with the gallium arsenide nanoantennas. And finally, I will show you how these nanostructures, which can be tuned by optical pumping, can be used for analog optical processing of spatially distributed light signal. So let me start with a brief overview of Me-resonant nanophotonics. In principle, this area work with small nanoparticles, subwavelength nanoparticles made of dielectric or semiconductor materials with high refractive indexes, which is typically low absorptive or even transparent in the visible or near infrared region. As we know from ME theory, these nanoparticles can provide both the electric and magnetic type resonances in comparison with metallic nanoparticles, which basically possesses only electrical one. And these resonances of electric and magnetic nature has more or less the same quality, which can be in principle used for designing of optical response of such systems. Combining these nanoparticles in different structures like oligomers or metasurfaces, we can provide optical response on demand. In principle, by tuning the geometry of these nanoparticles, we can achieve peculiar effects like zero reflectance with a full 2P phase shift with the nano antennas, and it's really important to design so-called metasurfaces. This nanostructure is composed of subwavelength nanoantennas located with the subdiffractive in the subdiffractive array, which can not only tune the amplitude of the transmitted light, but also can tune the phase of the transmitted wave. In principle, these metasurfaces can be applied for many different applications. During the last years, a lot of bright examples were demonstrated. Probably one of the most relevant is the meta lenses. They can be tuned in a wide spectral range, and currently even some startups are introduced in different countries which work with this kind of systems. Also, meta holograms, meta beam shapers was demonstrated. In principle, there are a lot of good benefits which can be achieved with the structures. Basically, they can be fabricated by standard CMOS compatible techniques. They can be done monolithically, so you can stack these nanostructures and provide good stability, good phase control, and so on. But one of the main problems which are still in the field, that we cannot effectively control these nanostructures after fabrication. So if we want to actively tune the structures, we need to provide some specific mechanisms for their reconfigurable optical response. And if we will look at recent papers, we can find plenty of different physical mechanisms which can be applied. For example, we can use liquid crystals to tune the transmittance or reflectance of these nano devices. We can apply so-called MEM structures to change, for example, the focus of the meta lens. We can use even magneto-optical effects to control the transmittance or reflectance of such structures. But as you can see, in principle, when we speak about this kind of techniques, we can control only some average characteristics like transmission or reflection, and it's really difficult to introduce some special control because it's hard to address a signal nano-resonator or nano-antenna in this metasurface on demand. So in principle, this problem can be solved with optical approach. I will show you on the next slide. In this work, I will focus on the mechanism of photo-induced optical control of these nanostructures. So in principle, you have a strong laser pulse which can be absorbed by the nanostructure, and this laser pulse generates free carriers inside the nanophotonic structure. This free carrier generation changes the refractive index and absorption coefficient of the material from which the nanoparticles is made. And it will change the optical response of these nanophotonic structures. It was demonstrated previously in many works for different materials, for silicon, for gallium arsenide, but as I already mentioned, in all of these works, people generally work with some average characteristics like reflectance in that case, but in principle they demonstrated that with this approach quite good modulation up to 70% and quite moderate pump fluencies can be achieved. But as I mentioned, if you want to change the spatial profile of the light beam, you need to provide some specific approach to address a signal non-antenna in the metasurface, for example. And it can be done by so-called asymmetrical pumping. So if you have, for example, two nanoparticles with different sizes, you can generate different plasma densities inside both of these nanoparticles. It will change the scattering profile of the system, of the non-antenna, and we numerically demonstrated that in principle in this system composed of two asymmetric non-antennas, we can change, for example, the angle of bending provided by this non-antenna under optical pumping. So in simulations we show up to 7-degree change, 7-degree bending, and in comparison with previously demonstrated results, for example for silicon, I will focus in this work on gallium arsenide, and I will tell you why in a few seconds. So for gallium arsenide in our simulations we achieved up to 10 times improvement in terms of energy efficiency for modulation. Why gallium arsenide instead of silicon, for example? We know that silicon is much more cheap material in case of fabrication, but gallium arsenide can provide, due to its direct band gap, it can provide not only the Drude effect. It's quite a simple effect when you generate free carriers inside the material, and these free carriers make this semiconductor, if the density is quite high, it makes this semiconductor like metallic-like. And in principle, this Drude effect works for many semiconductors like gallium arsenide, silicon, and so on. But in case of silicon, we can't achieve significant band gap effects like band gap shrinkage or band gap filling, which is quite significant for gallium arsenide, and it provides us much better control over the refractive indices and absorption coefficients of the material itself. So for experimental realization we decided to make a structure which is schematically depicted on the slide. In principle it's an array of non-antennas composed of supercells, so-called supercells. One supercell consists of 3 non-antennas with the same thickness of 200 nanometers, but the side length was different. So the first one had the side lengths of 120 nanometers, while the last one had 200 nanometers side. So we made it on purpose because when we changed the size of the non-antenna, as I've shown you on one of the first slides, by changing the geometry of nanoparticles, we can control its optical response. And in that case, we control the position of magnetic dipole resonance of these nanoparticles. And for example, for some specific wavelengths, in our case it was 835 nanometers, all of these nanoparticles have different scattering profiles and gives us different phase shifts when we consider the interference of the scattered field in the far field zone. So in principle it's like a diffraction grating composed of such non-antennas, but providing these phase shifts we can control the intensity in different diffraction orders. In our case we project the most part of the energy into the -1st diffraction order, and it occurs only in the case when we excite the magnetic dipole resonance in these non-antennas. To make the structures for experimental tests, we designed some experimental method or fabrication technique, so-called pre-processing technique. The point of this technique is that we first grow the gallium arsenide layer by molecular beam epitaxy, then we structure it with the standard approach like electron beam lithography followed by the refractive ion etching, and only then we transfer the structure onto the transparent substrate using a combination of different techniques like epitaxial epitaxial wet etching with the polishing and gluing on a transparent, some specific transparent glue. Also, we have some additional step with ALD deposition of aluminum oxide. It gives us better performance in terms of thermal stability, thermal and mechanical stability of the structure, providing us better experimental results. So for experimental characterization, we made an experimental setup which is schematically depicted on the slide. In principle, it realizes the pump probe method with additional filtering in the backfocal plane. So in principle, we have a femtosecond titanium sapphire laser with tunable central wavelengths and pulse duration close to 150 femtoseconds. So this pulse can be separated on two different beams. The first one with intensity 2 times larger than the second one. So this pulse generally pumps the structure, so it injects free carriers inside our non-antennas. And the second pulse, so it's probed. That's why we call this technique pump probe. But after that, this is not really typical for pump probe techniques. We use the objective lens with the high NA to collect all the diffracted light after the metasurface. And then in the backfocal plane of this objective, we can filter with a pinhole some specific diffraction orders after our metasurface. So in principle, we can measure signal in each of these orders. And also it was to mention that pump and probe beams were we provided a slight angle between these two beams to specially separate these two beams in the backfocal plane to provide better signal to noise ratio. Using this technique, in principle, we can characterize not only the pump probe and dynamic response of the system, but also the linear optical response that what we made at the first step. You can see this is the experimental results. So this one is for calculation. You can see that for 835 nanometers, we can see pronounced dip in transmission for the 0 order and increase in transmission of the minus first diffraction orders. So in principle, as we discussed, this wavelength corresponds to the magnetic dipolar resonance of each of these nanoparticles, and due to the excitation of this resonance, we redistribute energy between 0 and minus first and plus first diffraction orders. As you can see, calculation in principle quite close to experiment, and we can also prove numerically that indeed we can excite the magnetic dipolar resonance in each of these nanoparticles. But I want to mention that all of these nanoparticles are of the different size, and that's why the absorption are different. So we generate different plasma densities in each of these particles, which we can estimate also. This is the density for each of the nanoparticles. So in that case, when we excite our structure, we change the phase and amplitude profile of our supercell. It leads to redistribution of the energy between different diffraction orders. You can see that the the 0 diffraction order goes down, while the plus first and minus first diffraction orders goes up. So in principle, the characteristical time of this modulation lies at a few picoseconds, and we achieved modulation up to 16% with very low pump fluences of 5 microjoules per square centimeter. This concept also can be applied for another applications. For example, we can use these asymmetrical non-antennas to couple light onto the optical chip with some tunable response. let's consider a system which is depicted on the slide. We have a nano-antenna composed of 2 nanodiscs made of gallium arsenide with different diameters. We have a slot waveguide and some decoupling grating to trace the modulation. The idea is the same, so you can excite this nanodimer and you generate different types of different densities of free carriers inside these nanoparticles, changing the scattering profile of nanoantennas. So you can tune the angle of scattering and change the efficiency of coupling of the incoming light to this slot waveguide. In simulation, we demonstrated up to 30% modulation of the transmission when we excite the system with quite low pump fluencies, pump intensities up to gigawatt per square centimeter. We also made an experimental sample with a little bit modified experimental technique. Experimental results for linear transmission are in a good agreement with our numerical predictions. Currently we're measuring the dynamic response of the system. I hope that results will be also promising. The last project which I want to share with you today is analog optical processing of special light signal with this kind of metasurfaces. So in principle, the idea is quite straightforward. You know that lens, in principle, provide the Fourier transform, special Fourier transform in its focal plane. And if we will place some amplitude and phase filter in this plane, you can provide some processing of the incoming light. In principle, like in this picture, you can provide, for example, the first derivative or integration or even convolution. It can be used, for example, for application like edge detection, which is quite popular in the field of machine vision. In some machine vision applications. And of course, previously it was done for refractive, bulk refractive classical systems, but with metasurfaces it was done only recently. So we decided to use the same concept for our own work. So we investigated the optical correlator. So optical correlator in principle, like a classical scheme, is also quite straightforward. You have an SLM, it's a special light modulator that can change the phase of the refractive light, of the reflected light. And so the principle is following. You have some incoming image. You have Fourier transform of your reference image on the SLM, and in reflectance you achieve after the lens you receive correlation peaks corresponding to the reference image, which can be traced on the input image. Like in that case, on the right you can see the input image of X and O symbols. On the SLM we see the phase mask for the reference O symbol, and not so good, but anyway, on this output plane we can see some correlation peaks, intensity peaks corresponding to O symbols, which can be located on this input image. We decided to change this SLM in the scheme and replace it with our metasurface, a specially designed metasurface made of silicon at the first stage. So in principle, metasurface not only can reduce the size of whole system and make it more compact, but also it can provide both the amplitude and phase modulation, contrary to SLM, which typically works only in one of these regimes. So we designed a metasurface based on silicon nanodisk with different sizes and spacings. We encode in our metasurface the reference image of symbol H, and we demonstrated first numerically that when we have different images at the input of our system, we can see the clear correlation peaks at the output where our reference image can be located, even when different symbols are present at the input image. Then we fabricated the sample considering this design made of hydrogenated amorphous silicon on silica substrate, and we demonstrated in principle that this meta surface really can be used for such kind of applications. But as you can see, when you change, for example, the angle of the input image, the correlation performance decreases. So in principle, you need to trace your reference image as well. But for that purpose, you need some tunable nanophotonic structures, and that's why we decided to implement our previously discussed mechanisms to make some semiconductor metasurfaces made of gallium arsenide for active Fourier filtering with metasurfaces. So we designed metasurface which in passive regime without pumping provide the first derivative Fourier plane, and under optical pumping is provide only unitary transmission, so you can switch between two regimes. For example, you can detect edges on the image, and at the second, when you pump your system, you can just see the whole image, for example. So I want to conclude. We demonstrated sub-picosecond modulation with gallium arsenide optical metasurfaces of intensity in different diffraction orders. So we achieved 60% modulation in projected diffraction order with a very low pump energy of 5 microjoules per square centimeter. It's at least 40 times more efficient in comparison with previously achieved experimental results. Also, I've demonstrated how this approach can be used to, for example, provide some nanophotonic structures for tunable coupling of light onto the optical chip. And finally, I show you how this gradient metasurfaces can be used for analog or optical processing of special light signal. So thank you for your attention. I will be glad to answer your questions.
Thank you for a nice question. Thank you for a nice talk. Time is over. Please, only one question. Okay, please.
As you've shown in the beginning of your talk, your structure reminds very much optical phase modulator. So if you have, for example, a real optical spatial modulator, you can govern by each pixel, by voltage, for example. Yeah? In your case, you have very bright optical beam. In optical spectral region, that it means that you are restricted with diffraction limit of the light. So I do not see any big advantage before if you compare with optical phase modulator. Your device can work as a switch, for example, or you should compare with some image which was prepared also by, for example, lithography. Yeah? Can you comment probably?
Yeah, sure. It's quite a good question. Thank you. I will. So in general, I have a few remarks about your question. The first one, as I already mentioned, SLM can work only one regime. For example, basically, if we consider the liquid crystal SLM, it works for phase modulation. For example, you can also use some micromechanical mirrors to provide some amplitude modulation, but it's really hard to provide both the amplitude and phase modulation. And for example, in applications like optical correlation detection, it's quite important to have both the phase and amplitude mask, because if you have, for example, only phase mask, like in that case, your correlation efficiency really decreases. So you need to provide some specific tricks to make it much better. In our case, with metasurface, we can achieve both the amplitude and phase control at the same device. So that's one benefit. The second benefit is that, in principle, this metasurface can be done in the CMOS compatible way. So it's scalable, it can be fabricated in mass production, and the final price of this metasurface, which can be placed, for example, right on top of the CMOS sensor, will be very, very cheap. Comparing with SLM, typical SLM costs, for example, $5,000, for example. So your point that in SLM you can control the phase mask with some electrical contacts is right. In principle, in metasurface you can also provide the same functionality. But for example, for some cases you don't need to change, for example, like in the case when you try to find edges on the image, you don't need to change the phase mask. So in principle you can make it once and use it.
Maybe very short question. If you
Yeah,
compare the price, please do not forget the price of femtosecond laser.
No, no, no. I don't tell you about the tunable nanophotonic structures. So I tell you about the silicon metasurface which can be done, which can be fabricated right on top of CMOS sensor. I don't tell you that this metasurface will be active. So for some applications it can be passive. For example, for image edge detection. You don't need to actively tune it. So in principle,
my talk is slightly different from this section. I will not talk about plasmons, nanoparticles, or metasurfaces. I am going to talk about cold atoms, and I try it interesting for you. Okay, and in the beginning of my talk, I'll give you some brief introduction to atom interferometry, because our laboratory works with cold atoms and try to construct quantum sensors based on cold atoms. Okay, and when I will talk about quantum sensors and fields where it can be used, and describe where atom chip technology which we use in our lab, and say several words about the first Russian atom chip, and give you some experimental results. Okay, if you have some refractive medium and we want to measure the refractive index of such medium, we can use laser radiation. But if we want to do it with high precision, we need to use interferometer. And in this way, detecting the interference pattern, we can determine the refractive index of medium. In the same way, we can use, instead of a laser, atoms. But in this case, we need to construct atom interferometer and detect interference of cold atoms. This gives some advantages, and to do such interferometer, we need to use interaction of atoms with laser pulses. For example, to split atomic ensemble, we need to use half-P pulse. For mirror, we need P pulse, and again for the last beam split, we need to use again half-P pulse, and in this case we have atom interferometer analogous to a classical light interferometer, and in this case we can detect interference pattern on the output of such interferometer, and this interference picture will be depends on the phase shift, and the phase shift will be proportional to the angular momentum of such rotation of this interferometer. In this case, we can make some gyroscopes or to acceleration with term, and in this case, we can make some accelerometers or gravimeters. Such interferometers can be used both for fundamental and applied problems. For example, for fundamental research, it can be used for test of general relativity, detection of gravitational waves, and dark matter interaction. In case of applied problems, it is very interesting for navigations problem, geophysics, construction of gravitational maps, geology exploration, and such devices may be set on various movable platforms, such satellites. Okay, here you can see some example of atom gravimeter, which used called atoms in the conventional, which cooled down in the conventional 3D magnet-optical trap. This is commercial setup of company MIC-1s, and atoms from magnet-optical traps fall down in the gravitational fields, interact with half P pulse, P pulse, and again with half P pulse of laser radiations, and due to phase shift due to gravitation interactions, now we can estimate gravitational constant, and sensitivity and accuracy of such devices are very high, and now this device can be used in real fields. For example, this is detection of gravity change due to rainfall near the lake in the France, and here such device was used to detect gravitational change due to magma moving near the Etna volcans. Okay, such devices can be used in space. For example, the Project Mars, where the first Bose-Einstein condensate was realized in the space. And now on the board of International Space Station, there is such called atom interferometer. Here you can see the picture of Bose-Einstein condensation, which formed on the atom chip of such setup. Okay, the last example of atom interferometer, which can be made, which is very interesting for us, is atom clocks. And in this case, atoms which trapped near the atom chip can be used as atomic clocks, and they can interact with microwave generations. This is an optical transition of, for example, rubidium atoms, and detecting the Ramsey fringes of such atoms, you can construct high precision atomic clocks, and you can see that demonstrated stability of such clocks is very high, and it's higher than conventional CPT clocks, which are used today. Okay, what is atom chip? Atom chip, to construct atom chips, we need start from a dielectric surface, and on the surface of dielectric we need to make metal microwire, and we need a high current of about several amperes, and due to this current near the surface we can form magnetic field, and if you have additional homogeneous magnetic field, we have minimum potential of magnetic field near such microwire, and in this minimum of potential we can trap cold atoms. The temperature of such atoms can be down up to several tenths of nanokelvins, and it is possible to realize Bose-Einstein condensate near such surface. And here the scheme of our experiment is similar to our schemes with which used in Mayos projects on the International Space Station. And here you can see atom chip. Atoms cool down near the surface of atom chip with laser radiations, but to increase the speed of loading of such atom chips, we use additional conventional 3D magnet-optical trap, which forms low velocity atomic beam, and these atoms cool down and traps near the atom chip. In case of gravimeter, we need to switch off atom chip. Atoms start to fall down in the gravitational field and interacts with half p and half p pulses. In case of atomic clocks, we need to organize interaction of trapped atoms with microwave radiation, and in case of Ramsey scheme, we can register Ramsey fringe and stabilized microwave generator on this picture. Okay, how to cool down atoms near atom chips? Because of some problems with optical paths, for this aim, we used so-called mirror magnet-optical trap. You need only 2 pairs of laser beams. One pair is go through perpendicular to the screen, parallel to the surface of atom chip, and another laser beam goes in this direction, reflects from atom chips, reflects back, and reflects again from atom chips and go in this direction. And to construct the desired magnetic field distribution, it is possible to use magnetic coils, but if you want to construct a compact device, you don't have a lot of space, and in our case, we don't use this magnetic coils. In this case, we can use additional mesoscopic structures, for example, as Maya's projects, to make a magnetic field here. But from a technical point of view, it is very hard to make some atom chip, and in our lab, we decide to use only currents through microwires of atom chip, and because of this, we use a single layer atom chip. It is, from our point of view, it is more robust for future devices. Our atom chip consists of metal surface, and there is small slits between the microwires here. And there are 2 types of microwires, blue one and green one. Now, if the current flows through a blue wire, we have a magnetic trap, which is similar to the ordinary Jofa-Pritchard potential. And in this case, we can trap cold atoms and cool down it up to Bose-Einstein condensate temperature. But to trap atoms from thermal atomic beam, we need an additional stage, such as U-trap. And in this case, we have additional current here, and some current goes through U-shape, and the magnetic field from such configuration of currents is similar to a conventional 3D magnet-optical trap. Okay, here this is some model of our atom chip. Our atom chip is placed on the cuprum based, and the big problem for us is the current. I told that we use several amperes of current, and this is in case this chip works in the high vacuum, and there is no heat flows from the wires. Here you can see a huge heating of microwires, and you need to organize effective heating flow from the surface of atom chip. Here you can see the calculated temperature distribution for our atom chip, and you can see that the maximum temperature is about 150 degrees, and in a real experiment we measure 130 degrees of Celsius, and this is much smaller than the melting point, and this can be work in continuous regime, and this is some record for atom chips.
Okay, now you can make those 3 ampere through microwires in vacuum, and you can see here the calculation of magnetic field distribution near atom chip, and you can see that there is a small point where the magnetic field is 0, and there is some gradient of magnetic field in the x direction and in y axis, and of course in z direction, and because of this gradient of magnetic fields, we can use laser field to cool down thermal atoms near the atom chip. This is the photo of our atom chip. This is the first atom chip in Russia, and this chip was constructed in collaboration with Moscow Institute of Physics and Technology, and here you can see some electronic microscopy of microwires and surface of our chip. Our atom chip placed on the cuprum base and the vacuum flange, and the vacuum flange placed in the vacuum chamber. This is for this flange, and here you can see the vacuum chamber with conventional 3D magneto-optical trap, and which forms low velocity atomic beam for loading of atom chip, and here we placed so-called two-dimensional magneto-optical trap for future focusing of atomic beam. Of course, this is only photo of vacuum chamber. To do all experiments, we need a lot of mirrors, laser beams, CMOS cameras, and so on and so on. This is the additional magnetic coils. This is a photo of a real setup, and this is the scheme of a laser part. And here you can see the results of our work. And we have about 10 to the 6th, 10 to the 7th power of atoms with temperature about 200 microkelvins, and this is a photo parallel to the chip. And if we look from the down side, you can see the microwires of atom chip, and here, after background substrate, clear picture of cold atoms. The concentration of cold atoms is about 10 to the 10th power, and it's limited with the process of photoassociation in this cloud. And now we work on the new generation of atom chip to increase the number of atoms with the goal for Bose-Einstein condensation of such atoms. Okay, if we have cold atoms in U-trap, it's similar to the conventional magneto-optical trap, then we can switch off additional green wire and make a configuration of magnetic trap. And in this case, atoms trap without laser beams, using only currents through microwires, and you can see time screens, times dependent photos. In the beginning of working of magnetic trap, there are a lot of atoms in the zone near the atom chip. When we have two clouds, this one and this one, I don't. And these one atoms which trapped with magnetic trap, and these atoms fall down in the gravity. And after several milliseconds, only atoms trapped in magnetic traps stay near the atom chip. Okay, and at the end, there is a problem. If we want to construct effective quantum sensor, we need to load atom chip as fast as possible, and the
intensity of atomic beam in the region of atom chip is very high, but the problem is if you use a low velocity atomic beam, the radius near the atom chip is very high, and we decide to use element such two-dimensional magneto-optical trap, which can be used as a focusing element. And this is our theoretical prediction that in this case we can increase the loading factor by more than 2 orders of magnitude. Okay, at the end of my talk, in our lab we work with cold atoms, and we are the first laboratory in Russia which works with atom chips, and such approach can be used to construct quantum sensors which can be placed in future on moving platforms, for example satellites or aircrafts, and in this case high precision and high sensitivity to gravity or atom close can be realized. Thank you for your attention.
Anton, thank you for your nice talk. Please, questions to the speaker.
May I ask a question?
Yeah.
Okay, Anton, thank you very much. It's Andrei Naumov. I have a concrete question. When you have an experimental temperature 130 degrees, what was the maximal current in your structure?
The maximum current through microwires?
Yes, yes.
It's about 3 amperes. Now we have next generation of atom chip, and we can carry out about 10 amperes through microwires.
And this is chip with passive cooling, yes? You have not any additional devices for cooling like Peltier elements? Or
yes,
so
it's only passive cooling because you can't place such active elements in the ultra-high vacuum chamber.
Vacuum chamber around the structure, yes? Or why you cannot use, let's say, Peltier element?
You can't, as I know, Peltier it's not compatible with ultra-high vacuum. It's
okay, I see. Thank you.
Any other question? Anton, does the original idea of atomic cooling by using the wire, the huge current in the wire, belong to Schmidtmeyer?
Yes, Schmidtmeyer, Vollmann, and one of the first experiments was made by Hench.
Okay, thank you very much. Okay, the second question is by Andrei Fedotov. Sorry. The next talk is by Andrei Fedotov from Moscow State University, please.
Well, thank you for introduction. And firstly, I would like to share some personal information. For me, this talk is the first for last 3 years. Because firstly we had restriction connected with COVID, and now we have very huge problem with political situation. So I'm very grateful for organizers for their efforts for keeping trying to support scientific communication and for their efforts to making this conference. Thank you very much for program and organizing committee. And this work has been done at Moscow State University, and it connected with problem with generation and application of extremely short laser pulses, which has time duration around single pulse duration. For sure, it's very interesting fundamental application of such pulses when you have an opportunity to hit only one or two times during pulse and to interact with two folder interaction with matter. So it's very interesting fundamental applications such as attosecond generation or phase control of current and semiconductor or in metals. The problem, we have two problems in such area. Firstly, how to generate such pulses, and the second one, how to apply them. For such tasks, we can apply such very short waveforms. There are few methods to generate single cycle waveforms, such as coherent optical wave synthesis, broadband nonlinear optical, I just already showed you all my talk. And broadband nonlinear optical parametric amplification and spectral broadening in nonlinear medium, such as, for example, hollow core fibers. And in our case, we used this technique. Experimental setup is quite simple. We used more or less standard TiSAFA laser setup, which is based on master oscillator, TiSAFA regenerative amplifier, and home beat optical parametric amplifier, which can produce pump and signal and analog pulses tunable from 1 to 2 micrometers with an energy level 100 microjoules and with a duration around 50 femtosecond. Then we use signal or analog beams to pump hollow core photonic crystal fiber to generate single cycle pulses. And then for sure it's necessary to characterize such pulses and finally to use them for spectroscopic application. For nonlinear optical processes, and we choose hollow core photonic crystal fiber and revolver type photonic crystal fiber, which has capillary with rather big 200 microns diameter and filled by 6 smaller thin-walled capillaries. And this structure operates like a Fabry-Perot anti-resonance structure and support transparency band from 1 microns, 1.3 microns up to 3 microns. But it's really multi-octave band. And moreover, it's very important that in this region, such structure have negative dispersion, which helps to support soliton propagation regime. And for us, it's very important, soliton sun compression regime. Firstly, we have two main phenomena: self-phase modulation on the first stage of propagation of pump light in a fiber, and the second, it's when the spectrum is broadening, and on the second stage, because of the presence of negative dispersion, such broadened pulses can be compressed up to a very short waveform. And the problem how to control, how to characterize such waveform. So we used also home beat scheme based now on spider technique. It's a little bit modified spider technique when we perform interference not in spectral domain, not in time domain, but transfer it to space domain. And it's possible to observe interference of two spectrally transformed replica of very short pulses and to observe interferogram on just more or less simple CCD camera and to characterize pulse duration of such pulses, over pulses. So here you can see results of our experiment. By changing the pressure inside the hollow photonic crystal fiber and changing the parameter of a pump radiation, it's possible to broaden the spectral and finally to compress it. So here you can see that initially we could reach results up to less than 10 femtosecond. Just as a pump wavelengths, we used idler beam from OPA system, so it's around 2 micrometers. So it's still around one cycle of a field for these wavelengths. The very important question for single cycle waveform about absolute phase. So it's so-called carrier envelope phase and carrier envelope phase stabilization. For signal pulse, for signal output of OPA system, the phase is unstable and jumped for more than 2 pi, But in case of idler radiation, it's originally has passively phase stabilization. And here by using F2F interferometry, we could show that stability of the phase for idler path is quite high, around 100 milliradians. So it's really, you can see with short movie that the pulse is really stable in absolute phase. And moreover, we can control this phase, this absolute phase, by adding some feedback to last stage of OPA, optical parametric amplifier. We can control and shift with absolute phase. And here we can see the picture of the shape of Moscow State University. And actually, it's the shape of Moscow State University of shifting of phase of single pulses, around single pulses. Probably it's one of the best picture of Moscow State University, in scientific manner. And eventually we use such pulses and to tune some parameters and to measure propagation processes in hollow photonic crystal fiber. And our best result for nowadays is you see time duration around 6 femtosecond, that corresponds 1-to-1 single pulse waveform. And the power, peak power of such pulses is around 1.5 gigawatt. So what we can do with such pulses? The next step is to apply it for spectroscopy, or one of our goals is to control motion, to control current inside semiconductor to create really fast optoelectronic devices with petahertz rate. And as concerned to spectroscopic application, recently we developed methods of controlling of landscape of energy structure of semiconductors by means of harmonic generation, high order harmonic generation. When we can observe third, 5, 6, and so on harmonic generation from infrared pulses, femtosecond pulses, and by changing the intensity, changing the pump level of pulses and controlling the response of harmonic and nonlinear, so it's nonlinear processes. The idea is very simple. We can we can drive electrical electrons in brilliant zone. So if an energy of a pump pulse is high enough, so it reaches the band of a brilliant zone. So here it's really nonlinear area. So this nonlinear area gives high order harmonics. And just applying very simple Fourier transform analysis, it's possible to actually retrieve the form of such brilliant zone in different direction, but in this case, the pulses were not so short, few cycles, 3 or 4 cycles. So we did it before. So what can we do right now with more shorter pulses? And here there is a comparison of harmonic generation in zinc selenide, a very thin plate, and in case of more or less short pulses, more or less, I guess, 3, you see around 90 femtosecond or even less. We have separate peaks correspond to different harmonics. But in case of, let's see, very short pulses, all harmonics merge. No, it should be. It should be actually because the spectral bandwidth of a pulse is very short. So probably for this type of spectroscopy based on harmonic generation, such short pulses is not very good. No, at least it's necessary to make new investigation about applicability of such pulses for spectroscopy, in such manner for high order harmonic generation. Now here another example of influence of changing of absolute files of single pulse generation for supercontinuum generation. So it's the results actually very few weeks results, I would say. In the field of in the area of third harmonic generation, we could observe influence of changing of absolute files over pulses for the process of the third harmonics. Actually, I will proceed to conclusion. I guess we resolved the first task. So for creation of a source of single cycle waveform. So here it's the time duration of our pulses around 6 femtosecond for, and with rather high peak intensity. And we showed the applicability of such pulses for spectroscopy application, but it's still, at least we notice some influence. But to see what will happen, we'll see in the future. Thank you very much for your attention.
Thank you for your nice talk. Please, questions to the speaker.
May I ask a question?
Yeah.
Okay, Andrei, thank you very much. Very nice talk. I have a question about high harmonic generation in solid. The values of power you showed, power density, terawatts per square centimeters, it looks huge. Is it reasonable for a real experiment or not? Can you comment this value?
For sure, we control the damage threshold of our sample, and we still below the damage threshold. It's very important to be near the border of the threshold, because for sure we need very high intensity to pump electrons in the brilliant zone. But for sure we have to control that we still below the threshold. So it can be done by changing the focusing of the pulses to the sample. So it's not very difficult to control the damage.
Okay, thank you. Thank you for answering. Thank you.
Okay. Any other question? In atosecond science, it was popular so-called three-step model. In atosecond science, it was popular so-called three-step model. The idea from Paul Gorkum, from Kuchiev, when atomic target was irradiated by intense femtosecond laser pulse, the first step, ionization. The second step is acceleration of the electron to huge energy and recollisions with the parent ion, quick recollisions and a burst of attosecond pulses. The question is the following: to what extent it's possible to use the ideas of this simple man model to your results, or it's quite different?
No, the answer for your question is here. So it's the Gorkum model of nonlinear processes of free electron. When due to tunneling of electron for continuum, when it takes some energy by the field and then goes to a parent ion. Yes.
Yeah.
So because here we have only very short interaction, a very short tunneling time. In this case, it's possible to generate attosecond pulses. So you see here the idea is quite old from the Baltushka group. So you see, you're absolutely right. It's applicable for such experiment, and it's already there are some experiments in this case.
Okay, thank you very much. The next talk is Sergey Bedin, third spectroscopy on microcase of metal coating of track-edge membranes, Moscow State Pedagogical University, Lebedev Physical Institute, Center of Crystallography and Photonics. Please.
Good morning, colleagues. Today I want to talk about a simple method for fabrication series subsets based on metallized track-edged membrane. First, a few words about track-edged membrane. So, track membrane is polymer film with system for calibration pores. Pores are made several stages. At the first stage, the polymer films is radiated with ions in its cyclotron. After that, the polymer film with latent tracks is etching in alkali solution unit pores at format. The result is polymer film with system of calibration pore. Pore diameter from 50 nanometers to several micrometers. The surface density of pores is 10 to 9 power pieces for square centimeter. The main purpose to search membranes is filtration, laboratory and industrial filtration, water purification, separation of fluid components, and other. Separated area of application of membrane is template synthesis. This will be next report. Mechanical property is track-etched membrane is important for most application, in particular during the produce of metallized membranes. This was a problem of delamination of metal from the surface. We reviewed this one in the document physical chemistry. Now, for a few words about how we metallized the membrane. To this, we used the vacuum post for thermal film deposition. With this method, we can deposition copper, gold, silver, and nickel on the membrane surface. As a result, a membrane is obtained on one side of which does not carry thin layers of metal with thickness 50 to 100 nanometers. To study the elimination of metal coating, we made a mini tensile test machine on a 3D printer. This allowed us to observe the process to destruction of metal on the membrane surface in real time using optical microscopy. This slide shows a view to a track-etched membrane with a metal coating depending of deformation. It can be seen with increased deformation, the number of cracks on the membrane surface begins to grow. If compared to track-etched membrane with conventional film without pores, we can see that cracks are formed, but they are few and large in size. And we had an idea. It's possible to use metallized track membrane as a search substrate. When a membrane is stretching, a system cracks is formed with small deformation. The distance between cracks edges is very small, several nanometers. Gap hotspots we formed. We cracks from pure metals as exposed. We prepared sample of membrane with metal coating for research according to a follow scheme. Few using a tensile test machine, we stretching the sample to decide this deformation. When the test substrate was applied as a test substance, we used malachite green is various concentration, and after solution dried, we looked at Raman spectrometry on our sample. In this work, we used track-etched membrane with pores of 100 nanometers and surface density of pores of 10 to the 9th power of pores per square centimeter. Some photographs of a sample are presented on the slide. It turned out what the intensity of Raman spectrum depends on the magnitude of a deformation, and when larger it is, the greater the intensity of the dye signal we see. The change in the intensity of search spectra upon removal of a deformation looked somewhat unexpected. It can be seen what intensity increases with deformation and formation of cracks in the metal layer. When the deformation is removed, the intensity is the spectrum at the initial moment decreases, but after a while the intensity starts to rise again. This probably due to the fact that the cracks close and malachite green molecules fall into a small gap inside the cracks. It's worth paying attention to the fact that with all deformation, the membrane retains its filtration property. At the same time, saturation is observed at which the excess solution does not concentrate on the surface, but passes through to the pores. In conclusion, I would like to say that we have shown how conventional track membrane can be used at search substrate using a simple technique. Details of this work you can find an article in the journal Chemical Physics.
Thank you for your talk. Question, please, to the speaker. Okay. Please.
Did you control the homogeneous of your sample? So does search signal is the same from any points of your membrane? And then this, how did you control the position? So you stretch the membrane, then release it, and you expect that you measure the same position.
Control also dots membrane and
So first question, is the search signal homogeneous in any position
yes,
of membrane? Homogeneous. Then the second question, how did you control when you stretch the sample? Are you sure that you are measuring the same position?
Okay. Please to the last talk. The talk is given by Elizaveta Kozhina. The scientific team is from Lebedev Physical Institute and Moscow Pedagogical State University. Please go ahead.
So, good afternoon. I would like to talk about the ultra-sensitive search-active sensors based on linear silver nanowires bundles. And this topic is headed by Andrei Naumov. Firstly, I would like to mention that Raman scattering itself is a powerful method for identification of certain organic compounds in complex organic solutions. But unfortunately, due to its naturally low intensity signal, this method is locked in the scientific laboratory's walls and doesn't widely used in our everyday life. But now modern equipment allows to integrate so-called enhancing surfaces in such equipment, and probably in near future, thanks to the search-active substrates, there will be a compact equipment like glucometer based on Raman scattering method, and we may use this method in our everyday life. And also this opens up doors for such direction as identification of prohibited and dangerous substances in railway stations or airports, also enhance the level of study of cell and tissues, biochemistry in pharmaceuticals, and also allows to verify the authenticity, for example, of state of arts. So we grow the search-active substrates based on track-edged membranes by electrochemical deposition. And finally, we have nanowires that vertically standard on metal base. And this method now is patented. And the point is that in the case when we grow silver or gold nanowires, there will be E field localization in the nanowire tips due to lightning rod effect. But we know from literature that in case when we have small gaps between nanoparticles, the enhancement of the signal will be more huge. So the question is, how may we control such nanowires in order to have small gaps between, for example, its tips? And it's possible without us, because helps to nanowires elasticity when the substrate is drying after synthesis. Nanowires are linear together by its tips and form so-called bundles that looks on optical microscopy and semi-microscopy as strips. So there are many nanowires that lean together by its tips. So there are many contacts between where we may achieve a gap hotspots areas. So the point is how we may control the molecule localization in such tips. So we are supposed to apply the analyte when substrates are wet, so not dry after synthesis, and in the case that when we apply the analyte that consists sulfur in its structure, that types of molecules will be adsorbed uniformly on silver nanowires, and after drying there will be a contact areas where molecules are located in the nanowire tips. Also we mentioned that there are dependence of the Serre's intensity signal on the nanowire's length, and this is because of the different formation of hotspots areas. For example, when nanowires are short, the elasticity forces doesn't enough to link them together, and there are no gap hotspots, only lightning rod effect is work. So enhancement of the Serre signal will be not enough. And when we grow long nanowires, then will be bundles consisted from dozens of nanowires, so there will be no possibility to achieve a contact point between their tips. So there is an optimal nanowire length when nanowires so-called medium, when only few of them are linked together. According to our calculations, our experimental enhancement factor is equal to the 10 in the 7 power, and the theoretical one is 10 to the 8 power. If we look to the modeling pictures, we may mention also that the enhancement in the gap area when the nanowires are not linked is equal to 21. And theoretically, the Serre's enhancement factor is proportional to the 4th degree of such numbers, and if we put that numbers in 4th degree, the difference between wet substrate and dry will be huge. And the question of what we may say about the reproducibility of the signal, as the signal from one point to another of Serre's substrates is the same. And to do that, we did the Serre's mapping over the large area, and we took the 600 spectra on such substrates and studied the different Serre's mappings on nanowires with a diameter of 60 nanometers, 100 nanometers, and 200 nanometers. The difference between such substrates will be again in the gap hotspots formation when nanowires with small diameter, they linked, there are hundreds of them from a strip. And there will be some characteristic strips in the Serre's mapping too. When we have 100 nanometers diameter, there will be some points where the Serre signal is enhanced, and when we have 200 nanometers, there will be only few areas when the Serre signal is enhanced. This is due to the fact that not all nanowires are linked together because the elasticity doesn't enough. To plot that mapping, we choose the area under the peaks and plotted this mapping over that area. And then we use the statistical analysis and plot the histograms over the area under the peak located in certain position, and here there is amount of spectra. Helps to statistic, we calculated the enhancing area percentage. So for example, when we have 16 nanometers diameter nanowires, the probability that we will have enhanced signal if we just focusing in random area will be equal to 59%, and this percentage will be lower when we have the nanowires of bigger diameter. And then we thought, what if we choose such areas when we have visible peaks, and plotted that areas, only that areas. And we have some segmented mapping, and if we choose the desirable areas, for example, 1 areas, 2 and 3, we may plot such segmented mapping and see noise, tip hotspots, and gap hotspots, so that areas where we that have small gaps between nanowires. It also should be mentioned that due to high contact area, we may cultivate a cell's structure on such substrates and study, for example, the drug delivery. The problem, there is one problem in spectra analysis, because spectra from such difficult structure very not only noisy, but there are too many peaks to analyze them. But now we try to do the mapping of such cells. Took, for example, 1,000 spectra and then analyze the spectra point to point from that cell before and after drug preparation. And now the question is what we may do next to enhance our source signal. And there was an idea to do the magnetic control of the linear property. And to do that, we put the ferromagnetic compound in the center of silver nanowires by analyte changing, and in that case, after magnet application, we will have the mechanical control of agglomeration, and the layered structures is well seen in some images. So to do that, to verify that that's work, we apply the Radoman 6G on such structures, and there is the intensity of different analyte concentration without magnet application, and we will see that it's 10 in the third degree. And after magnet application, we will have 1 magnitude more. So, for example, we may compare them in one graph, and it's well seen that the difference is really huge, not only in intensity, but also in the characteristic peaks registration. So that's all. Thank you for your attention.
Thank you for your nice talk. Please, question to the speaker. Okay, please.
Probably slide number 8, where did you show the intensity of SERS when you showed vertically aligned so wires and touching each other, 4 nanometers height of not this one, it's like previous one.
That?
You showed 4 monolayer height of no before earlier, not wrong direction. Not here. Further. 4. They should be 4. There was slide where you showed vertically standing wires and touching each other.
So
and 4 monolayer height. Not here.
But, well, that's the second slide.
Next one, next one, next. Yeah, here. Look here. You showed the height of the nanowires.
Yes.
Top, on the top schematical, 0.7 microns, yeah? And you compare with 4 microns, yeah?
Yes.
Difference is 5-6 times, yeah?
Yeah.
And intensity is also, difference in intensity also the same. Yeah, it means that the gaps doesn't work here. This is just the effect of the lens, right?
In that case, yes, and I told that this is due to the fact that too many nanowires are leaning together and it's not possible to achieve a point contacts. So there are not,
okay, but we
there is
see
no
on the images that they touch each other here, yeah?
Yes, but there are dozens of them. There are dozens of them. Not several nanowires, but dozens, bigger. Amount of nanowires are leaning, and here there is no possibility to achieve a point contacts because the angles at which nanowires are leaning are too big, and molecules couldn't
Then
relocate.
the images when you showed hotspots, you performed micro-Raman experiments, for example here, and saying that you see hotspot due to gaps.
Yes. It's
so
the next slide.
I'm not completely agree with you because your spot size is much bigger than the size of a hotspot. The size of hotspot is just several nanometers, even less.
Yes.
And you use micro-Raman spot, say 0.5 microns. How can you be sure that you measure in hotspot? So, to my opinion, this is not possible here.
I could not say that we measure exactly hotspots. We measure source intensity signals on the substrate. So, for example, we may suggest that in that area where nanowires are leaning, the source, the signal is more intense. So, this is area where we have hotspots. Here, yes, and the gap hotspot. So we suggest that there are areas where nanowires are leaning together, and so there is tips. And here, just areas when, side areas of such substrate nanowires, like side areas. And gap hotspot, it's point.
There is no proof.
Well, there is no proof, actually.
That you have hotspot, then you showed
I could not say that I suggest.
And just a moment, let me say. You should convince us that you see image, scanning electron microscopy image, and this say when these nanorods touch in each other, then show that exactly the same position you see enhancement of Raman scattering. Just only in this case you can say.
Okay.
Just from these images, to my opinion, I can conclude that you have just rough surface where you, in homogeneous sample, just simply, where you have different intensity of Raman scattering. And this is not obligatory related to this gap effect.
Probably.
Okay, any other question? Okay.
Dear colleagues, thank you very much for your attention.